All right, welcome to the 2022 SpecFem workshop for users. This is a virtual workshop, clearly. We're thrilled to have, at the moment, 148 people joining by Zoom. And my name is Carl Tape. We've got a team here from University of Alaska Fairbanks, as well as a team from Colorado School of Mines who are going to host this workshop. This workshop is being recorded and will be posted. And so we're going to start with some protocols on Zoom here, just to get us on the same page. And after that, we'll launch right into our talks. So I'm going to share a screen. Yeah, so this is going to be a pretty just couple bullets on Zoom, as I said, and then we'll have a slower introduction following our guest talks. So everyone has been on Zoom for years probably, but I just wanted to, every permission settings differ. So as I said, we want to interact with everyone and have a successful workshop. Here's some guidelines. Display your full name. This would be like wearing a name tag. You can right click or click on participants in your name, find rename, just have it whatever you want, but think about being at a meeting. Mute yourself unless you have a question. I don't know if this really matters, but we're suggesting to keep your camera off in order to minimize the bandwidth in the main room. But if you're speaking with someone, please turn on your camera. I really don't know if this matters, but we've had anecdotes of things like if everyone's camera for hundreds of people is trying to stream into certain internets, that may be an issue. Raise your hand if you have a question. We'll go through this slide. Ask your host or helper if you need to share your screen. This will be common in breakout rooms. If you have one-on-one, you can share a screen. If you're stuck, enter a breakout room that's empty, or you could post a chat to let hosts know you're headed there. We'll have people monitoring that. We've gone through this before, and we'll find you there, help you, hopefully, and then you can leave the breakout rooms. Just be prudent with the use of the main chat room. There's, 161 people here, so think about the questions that are more of a general nature. But anytime you're stuck, we'll have people monitoring that. And then I'll be sending poll questions like, are you ready to proceed? That'll gauge us on whether we're going too fast or not. All right, so just reminder that on the Zoom bar, you've got things like you can click on participants to see yourself in the list of people. You can control your settings from there. There are breakout rooms. There's reactions where you can like raise your hand. So you have all these permissions to mute or not, to share your video or not, to share a screen. So you have as many permissions as pretty much you can have, which is why it'll enable sort of freedom to speak around, but just beware of that. So kind of, we don't want to be like muting everyone wholesale, but I hope this is what we want, and we want to believe that this will work out well. So to raise your hand, click reactions, raise hand, and when you're done, lower your hand. Alternatively, you can type things in chat, but we welcome, just audibly asking questions is fine too. All right, and then there'll be a poll that says, are you ready to move on? Please answer that so that we can gauge whether to move on. And this is just the rename part. You can go in, click participants, rename, set your name there. Okay, so there's going to be basically a 2-slide introduction, and we'll kick off with the first talk. But I wanted to kind of start at a high level that those of us hosting this workshop, we're motivated to reach out to new and existing users of open source software, which is the SpecFem software suite. And so this is we'll get some overview of what this is, but I want to start at the top of, the main developers on the things that we'll be featuring today and over the next 3 days. Daniel Peter, Jeroen Tromp, and Rohit Kadar at Princeton here, KAUST. We'll be hearing from Jeroen and Daniel very soon. On the sort of iterative components of the software, we'll be looking at Ryan Modrak from Los Alamos, Brian Chow here. And then on the second level, sort of where did this workshop come from? The content is really almost entirely pulled together by Bryant with the strong support to enable this mode of delivery. Ian Wong at Texas Advanced Computing Center, building the containers that remarkably, in my view, work on the M1 Mac and all these other systems that we've tested. And if you don't have things working right now, don't worry. We'll have a chance, a 30-minute break where we can possibly help you out. I put some key links in here. I can share these slides later, but let's get right into it. So each day is going to start with a speaker. So day one today, we have Jeroen Tromp kicking things off. And then Daniel Peter kind of following on the theoretical of spectral element method with looking at really history of SpecFem. I'm very excited to see these, not really the kind of material you'd see at like an AGU session, for example. So I think it'd be a nice way to start. On day two, Chinya Liu from University of Toronto, as we move into the adjoint methods. And then Bryant, I've asked him to lead the talk on day three, sort of the application side and the iterative seismic imaging. So that's where we are right now. And I'm going to stop sharing screen. I think I will give you a longer introduction to this about who's covering chat and all these things, but I think let's just start with the talk and we'll kind of follow that with Q&A. And if you have questions, you can hit them in chat. We'll have people monitoring. So with that, Jeroen, thanks for being here. And I would say share a screen.
That working?
We're seeing more than the we're seeing kind of the, okay, there we go. Perfect. Thanks.
Okay.
Yeah, I would say, yeah,
Sure.
I sorry. Maybe just a quick introduction. Jeroen Tromp, Princeton University, and one of the two folks who brought together SpecFem and really brought it into the realm where we can share widely at the global level. So please kick us off here, Jeroen. Thank you.
Yep. So thanks, everyone. It's really a pleasure to be here, and it's wonderful to see so many people interested in these tools. I was asked to say a little bit about what SpecFem is actually all about, so the physics of the problem, and I will start with that, and then I'll also say a little bit about how we do optimization and inverse problems with these tools, although Chinya will cover that in greater detail tomorrow. So first of all, SpecFem solves the seismic wave equation. So that's the equation of motion. And in its simplest form, it sort of looks like this, where you have the density rho times the acceleration, where s is the displacement. And so dt ds squared is the acceleration, minus the divergence of the stress tensor is equal to some force that is exciting the wave field. So this is just F equals ma. And we need a constitutive relationship to solve this equation. And we do that by using Hooke's law. So Hooke's law says the stress T is linearly related to the strain epsilon through this elastic tensor. And for those of you who know a little bit of tensor calculus, that's a fourth order tensor that relates these two second order tensors. The stress and the strain are related through this fourth order elastic tensor. And remarkably, in SpecFem, that tensor can be completely general, which means that it can have 21 independent elastic coefficients. But most of the time, we just look at an isotropic material, in which case we have just two elastic parameters. But suffice it to say that we can deal with the full Hooke's law in these software tools. Then you need to have some boundary conditions, and the boundary condition we typically use is that the stress, the traction, so n hat is the normal to a surface, and you dot that with the stress tensor to get what is called the traction. So think of that as the force on the surface, and that needs to vanish. So the Earth is a stress-free surface, And so we implement this stress-free boundary condition. Then you have to have some initial conditions. So we typically use quiescent conditions where both the displacement field at time 0 is 0 and the velocity at time 0 is 0. And then the earthquake is represented by a force F. And typically we use a double coupled source, in which case there is a moment tensor M that represents slip on a fault. And then the gradient of a delta function where xs is the source location and s of t is the source time function. So this really is the full set of equations that needs to be solved if you want to propagate seismic waves in an elastic medium. And this is precisely what the SpecFem packages do in either 2D or in 3D. And in fact, they do much more than this because often there are additional complications. But in the elastic case, this is what the equations of motion look like. So that's the forward problem. Now, SpecFem doesn't actually solve these equations in the form that I just showed them to you, which is called the strong form, which is a differential form of the equations of motion. Instead, it uses what is called a weak form, which is an integral form of the equations of motion, where you can see here on the left, I've dotted the acceleration, rho dts squared, with a test function, vector really, w, and then I've integrated over the domain omega in which we're solving the wave equation. And then on the right-hand side, I've integrated the divergence of the stress by parts, so that I have the gradient of the test function, which is being double dotted or contracted with the stress tensor. So this is, for those of you who know a little bit about finite element modeling, this the stiffness matrix, which is also integrated over the volume. And then the source is just the moment tensor double dotted with the gradient of the test function evaluated at the source location times the source time function. So this is just a weak form of the equations of motion, and it's equivalent to the strong form that I showed you in the previous slide. So we can solve these equations either way. And so strong methods like the finite difference method or the pseudospectral method, these numerical methods work with the equations of motion in their differential form, as opposed to the finite element method, and in this case, the spectral element method, just a variant of the finite element method, which uses this weak form or integral form. And so one of the really important things to note here is that this weak method implicitly accounts for the stress-free boundary conditions. And that's really great because if you have topography and there's significant variations in elevation, that boundary condition you get for free in a weak method. And it's a really powerful thing because it means that scattering by hillsides or the propagation along some sort of a ridge, all of that can be modeled very accurately with this method, as opposed to the troubles you have with strong methods that get lots of staircase effects and other artifacts that are induced by trying to grid topography. Sorry. The second thing you get by using this weak form is that it's really straightforward and very mathematically elegant and also numerically elegant to couple different regions explicitly. So imagine you have a fluid and a solid region, which we have inside the Earth between the inner core, which is solid, and the outer core, which is liquid. And then again, between the liquid outer core and the solid mantle. And then again, between the crust and the liquid oceans. So fluids solid coupling happens all the time, and we need to deal with wave propagation in these coupled fluid solid domains. And again, it's very easy to take care of those kinds of interactions through these surface integrals where you get the opportunity to exchange the traction. So those coupling terms may be explicitly added, and that's another really important benefit of these weak methods. I should say that the technique as we use it was originally developed by Komatic and Vilot back in 1998, and then further developed by me and Dimitri together over many years with sort of the key publications here in 1999, and then in 2002, where we did wave propagation on a global scale. So what is the spectral element method? Well, as I said, it's a variant of the finite element method. So typically, although you don't absolutely have to, but we use hexahedral finite elements, which are just deformed cubes. And then within those elements, we use what is called Gauss-Lebattle-Legendre quadrature. So that's the quadrature rule that we use to perform these integrations that we needed to do in the weak form. And if there's anything that you should remember about why we are choosing this spectral element method to look at seismic wave propagation, it is that the mass matrix that you get when you do that is diagonal by construction. So if we think about the equations of motion sort of at an abstract level, we have again, let me see if I can annotate. No. No, sorry. I was trying to see if I can annotate, but it doesn't work.
Sorry.
We have the mass matrix M multiplying the acceleration, U double dot. So that's the first term. Then you might have some sort of a damping term, C multiplying the velocity, U dot, and then the stiffness matrix that we talked about times the displacement vector U equals the force. And the whole goal of the spectral element method is to make that mass matrix M diagonal so that you can just divide it out. And that means you get, from a numerical perspective, an explicit time marching scheme. So you can just march the system in time, and that's what makes it very powerful. So what is great about the spectral element method? First of all, it's a finite element method, which means all the calculations are local. And that means it scales extremely well on parallel machines. So there are no long-range interactions. So that's one really important thing. And the second is, again, this explicit time scheme and the diagonal mass matrix. So here on the bottom, you can see the interpolation functions that we use to represent fields on the element. So this is in one dimension. You have these Lagrange polynomials. Sorry. And this is how they vary along one side of the element. So if you look in the picture above, you have the red balls, which are the corners of a hexahedral element. So you see 4 of them there. And then the green balls in between are other GLL interpolation points. And these interpolants at the bottom right are the functions that oscillate through these GLL points and that are used to represent the wave field in 3D within that element. So you can see we typically use 5 by 5 by 5, so 125 GLL points within one spectral element. And this is how we capture the wave field. Sorry, now I've lost my. Okay. So over the years, we've developed these software packages that perform these calculations, and that's the SpecFem software suite, and that's what this workshop is all about, so that you guys can learn how to use these tools. And from the very beginning, Dimitri and I both felt strongly that the software should be open source and freely available to anybody. And so for years, we've used CIG, the computational infrastructure for geodynamics, to distribute these tools. And so SpecFem 2D, SpecFem 3D, SpecFem 3D Globe, they're all available through the CIG, and that's what you'll be working with over the next couple of days. So what these tools can currently do is they can accommodate fully 3-dimensional models of the crust and the mantle. They can accommodate topographic and bathymetric variations. The Earth is rotating, so I mentioned that the actual physics that these solvers can deal with is more complicated than the introductory slide that I showed you. We actually also take additional effects associated with rotation into account. You can make the Earth elliptical in shape, and we can deal with gravitation. Now, SpecFem 3D and SpecFem 3D Globe accommodate gravity in the cowling approximation, which means that it takes into account the background gravity perturbations, but it does not take into account gravity perturbations induced by the motion itself. This is something that we've recently addressed, and currently there is a full gravity version of SpecFem, and I'll make another comment about that in a minute. I mentioned anisotropy, so that's a directional dependence of the wave speed. To do that, you need this full elastic tensor C that I mentioned during one of the earlier slides. So in principle, SpecFem can accommodate full elastic anisotropy, 21 elastic parameters. Attenuation, of course, is an extremely important part of seismic wave propagation. I did not explicitly call that out in the slide that talked about the forward problem, but suffice it to say that is extremely important. This means that there's memory in the system, and you need to take that into account. So SpecFem can deal with that. And that's a really important complication that you must take into account if you want to do realistic simulations of full 3D seismic wave propagation. Then, very importantly, all the packages have adjoint capabilities, and I have some slides that talk about the adjoint state method. This is a crucial ingredient that enables you to do inverse problems, because it enables you to calculate numerically the gradient of a misfit function. Also, very importantly, all the packages are accelerated for graphics cards, and this is really something that we have Daniel Peter to thank for. Daniel spent his postdoc porting the software to graphics cards, and so all the packages that we have now are GPU accelerated, and I cannot overstate how important that development has been, because this is what has given us access to some of the fastest machines in the US, for example, at Oak Ridge. One little animation of products that are produced as a result of these simulations. This is from the Shake Movie website at Princeton. This is a magnitude 7 earthquake on March 9th in 2015 in the Eastern Pacific. And so the movie just shows you the up and down motion of the ground as a function of time. So you see these body waves, and now the surface waves radiating away from this earthquake. You can see some folding happening in these wave fronts as a result of the 3D heterogeneity of the Earth. You can see how the waves slowly circumnavigate the globe, and they will be focused on the other side of the Earth at the antipode. And I have another illustration for you that's work from Daniel Peter and Abel Bozak, where they actually use SpecFem to simulate seismic wave propagation on Mars. So here you see the waves propagating across the Martian surface. The topography of Mars is shown, and there you see that caustic. So these waves keep going and focusing and defocusing at the antipodes as they circumnavigate Mars. And so here, the variations that we're seeing are almost all due to just the topographic variations and the crustal thickness variations on Mars. Now, a couple of comments about recent developments. I mentioned the cowling approximation. We are just writing a paper on a full gravity version of SpecFem. That's work by Hamnath Garti with Leah Langer and Will Eaton. So that means we're now coupling conservation of linear momentum with the Laplace-Poisson equation. So there are opportunities for atmospheric seismology. In other words, we can couple the atmosphere to the solid Earth and look at wave propagation in the atmosphere, both acoustic waves and gravity waves there. And there are also opportunities for tsunami modeling. So tsunamis are gravity waves. And so we could add an ocean layer to the globe and look at tsunamis. Omnath also has developed quasi-static solvers. So these are solvers that basically throw away inertia. Now you, oops. Ah, it was too much for Keynote, this. Am I still sharing?
Not right now.
Okay, let me try again. Up. Yeah.
Looks good, yeah.
Okay, sorry about that. Okay. Quasi-static solvers, yeah. So you throw away inertia, you lose the mass matrix. So you might think, well, don't you then lose all the benefits of the spectral element method? But actually, it turns out that the quadrature is also extremely valuable. And so for these quasi-static problems, you can really do beautiful modeling with our tools. And that's the SpecFem X package that Omnath is responsible for. And if you're interested in such problems, then we can help you there too. The last thing I wanted to mention about recent development is that we are currently actively working on porting the entire software suite, including SpecFem 2D, 3D, and the globe, to what is called Cocos. And Cocos is a software development environment that is completely geared at portability and scalability. So one of the things that is extremely hard to deal with software like this is that it's always evolving. We are constantly changing and updating software so that it will run on the latest computers. And it's a never-ending task. It's extremely time-consuming. And so Cocos is an environment that should make that extremely easy, because it will always just run on whatever the latest system is that is available. So this is work by Rohit Katkodkar, and he is a research software engineer at Princeton, and I hope many of you will be in contact with him as he makes these new tools available to the community. Carl, shall I do this still, or would you like me to? I think you're muted.
You're still muted.
You're still muted, Carl.
I think he's having a Zoom issue, he said. He's going over.
Tell him to keep going.
He said, keep going.
Oh, okay. Okay, so then I promised you that I would say a little bit about the adjoint state method and optimization. So the way we do that within SpecFem is motivated by what is called PDE constrained waveform tomography. So partial differential equation constrained waveform tomography. And the way you do that is you have a misfit function that you want to minimize. So in this case, the first term says the synthetics at some station XR as a function of time, minus the data at that same station as a function of time. The least square difference between these two things we want to minimize. That's what's called waveform inversion, right? And then the second term says we want to minimize that difference, but subject to the constraint that we know that the seismic waves satisfy the wave equation. So in parentheses there in the second term, you can see F equals ma, right? Rho dt f squared minus the divergence of the stress minus the force. That's the wave equation. And that parameter lambda there, that is the Lagrange multiplier, the constraint that we are adding that says we want to minimize these differences subject to the wave equation constraint. So that's PDE constraint optimization. And if you go through a lengthy process of figuring out what the change in the misfit function delta chi then looks like, you get these three contributions. The first one is the model parameter density, rho. So that's one of the parameters that you can change. The second is the model parameter C, the elastic tensor. And finally, delta F, that's the model parameter that represents the source. So these are the three model parameters that we wish to constrain when we try to fit synthetic simulations to observed simulations, right? So our model parameters are, again, the density, rho, the elastic tensor, C, and the earthquake, F. And so this expression tells you how a change in the density, delta rho, affects the misfit, delta chi. And that sensitivity comes through this kernel K rho. And the same thing with delta C. The change in delta C is that produces a change in the misfit delta chi comes from this object Kc, which is the sensitivity kernel to the elastic parameters. And then finally, this last term, delta F, there your sensitivity is to this S dagger, which is actually the adjoint wave field. So the key here is, if we know what these sensitivity kernels are, K rho, Kc, and S dagger, then we can do an inverse problem, right? Because then we have a way of finding changes in these model parameters that might help minimize the misfit. We have a gradient of the misfit function. So this is what these kernels look like. This is K rho, the first one, and then Kc, the second one. And they have the same structure. They have, in the first instance, K rho, you have the acceleration dt ds squared on the right, being convolved, notice the big T minus T, with this adjoint wave field S dagger. And the same thing with Kc. There we just have the gradient of the forward wave field, grad S, being multiplied by the gradient of the adjoint wave field, S dagger. So the one thing that should be clear from this slide is that the solution to this problem clearly lies in this S dagger, this adjoint wave field. If we have this S dagger wave field, then we can calculate these kernels, and then we can do gradient-based optimization. So that's the key question now, is what is S dagger? Well, it turns out that the wave equation that S dagger satisfied is just the time-reversed Lagrange multiplier, lambda. And that means that the adjoint equation of motion looks just like the regular equations of motion, except with daggers. The adjoint wave field, the stress associated with the adjoint wave field, and an adjoint source. We have adjoint boundary conditions. The stress associated with the adjoint wave field attraction should vanish. We have adjoint initial conditions. The initial adjoint wave field and the initial adjoint velocity should vanish. The only difference here is the adjoint source. And that takes the form of the time reverse differences between the synthetics S and the data D injected at the receivers simultaneously. So let that sink in for a moment. It's an amazing thing that you can calculate the gradient of a misfit function by taking these time reverse differences between the simulations and the observations, injecting them at the receivers, and letting that be the source of your adjoint wave field. So basically, you're back projecting the errors, the misfit between the data and the simulations. And that wave field is the adjoint wave field. And of course, the beautiful thing is that these are the exact same equations as the forward problem. In other words, once you've written SpecFem to do the forward problem, you can use the exact same tools to do the adjoint problem. You just have to change the source. And therein lies the beauty of the adjoint state method. So it's a wonderful thing. So here's a little illustration that shows you how you actually construct these sensitivity kernels that are the key to doing optimization, right? To doing inverse problem. So this is a slide I borrowed from a paper that I wrote with Carl and Chinya. This is Carl's handiwork, and it's illustrating how the regular wave field behaves. So that in the box in red there, we're now focusing on the regular wave field, and you need to read the slide from the bottom left panel to the top, and the source is at the star. So what you see is this little wave field that, as you go up in these yellow boxes, radiates away from the star. The side boxes and the bottom box, the sides and the bottoms are absorbing boundary conditions, but the surfaces are reflecting boundary. So you see the wave field reflecting. And then once you get to the top, we see that the forward wave field, the direct wave S, has run over the receiver, which is the square. So that's the forward wave field running up in time. Now, the way you do that Then you make a measurement of the observed velocity in the rest box. That's the first arriving shear wave. And you turn it into an adjoint source. And that adjoint source now runs in the opposite direction. So starting at the top and running to the bottom. And we see it animates from the little box, which is the receiver. And we see the adjoint wave field radiating away from that box, reflecting off of the free surface and being absorbed at the absorbing boundary conditions, just like the forward wave field, but in reverse time. So here we have the solver running twice, once to generate the forward wave field, and now to generate the adjoint wave field. Now the interaction in the big red box here in the integral is the communication between the forward wave field and the adjoint wave field, and that happens at these red blips as you move from the top to the bottom, right? That's where the forward wave field and the adjoint wave field talk to each other as you perform this convolution. And when you integrate it, you get this sensitivity kernel, and in the bottom right, we see an example of a 2D finite frequency sensitivity kernel that shows you how the S wave is sensitive to the structure between the source and the receiver. Right? And that's the beauty of the adjoint state method. It is completely compatible with the banana donut finite frequency theory that was developed at Princeton by Tony Dahl and Guus Nolet. Right? These things are identical. In any case, there's your Fauché derivative. There's your density sensitivity kernel. So it says that if you make a measurement of this S arrival and you want to constrain the structure in the yellow box, you are sensitive to variations in that cigar-shaped volume in the bottom right panel. So that's the adjoint state method in a nutshell. So final slide is then, how do you do optimization? So we've chosen our misfit function. Now it doesn't have to be the difference between observed and simulated seismograms. In other words, you don't have to do full waveform inversion. In fact, we rarely do. In exploration geophysics, people often do. We focus on measuring different things, and different measures of misfit lead to different sensitivity kernels. But all of these things can be worked out, and there's a very nice paper by Ebru Bosdak that goes into the details of how you can formulate any measurement you like, any measure of misfit between data and synthetics, and figure out what the corresponding sensitivity kernel is. So it's really important to realize that the kernel reflects your measurements. Okay, different measurement, different kernel. Now, if we expand this misfit function around the current model by adding a perturbation delta m, you can write it as a Taylor expansion. So you get chi at m, you get the gradient g of m times delta m, and then the Hessian h of m times delta m from the left and delta m from the right. So it's just a Taylor expansion. And so you try to do the model update where the gradient vanishes. In other words, you want the gradient at m plus delta m to be 0, because then you've taken a step where you are at the bottom of your misfit function. And if you use that criterion, that requirement says that the action of the Hessian 8s at your current model on your model perturbation delta m should be equal to minus the gradient of the misfit function. Okay, and that's a quasi-Newton method. So this is what we want to solve. Sometimes people use a gradient update. So that's like a steepest descent, in which case the model update you take is in the direction of the negative gradient, minus lambda g. That's a gradient method. You have other options like precondition conjugate gradient methods, which have some memory in terms of taking into account previous descent directions. But these days, we heavily favor the LBFGS quasi-Newton method, which really tries to solve H delta m equals minus GM. So with the solvers now and the adjoint capabilities, you are in a position to get the ingredients that you need to solve these inverse problems iteratively using these types of optimization methods. That's all I have for you.
Thank you, Jeroen. We'll give the Zoom hand clap or audible ones. And the segue there is that the plan is that you will be doing exactly that, running LBFGS on synthetic toy problems day 3. But anyway, yeah, thank you very much. And at this time, I know we already kind of off the scheduled agenda, but we're not that far off, and we're really going at whatever pace is best. And so what I'd like to say now is, if you have a question, please raise your hand, click on reactions, raise hand, and ask a question just like you would in a lecture hall with 185 people, except you don't have to yell. So yeah, if you have a question, we'll just start there. Go ahead, Jordan. You'll have to unmute yourself probably.
Hi, can everyone hear me?
Yes.
Great. I like the point about the strengths of the weak form of the equations of motion and solving that with the spectral element method. What would be the relative advantages of the strong form compared to the weak? Is it conceptual simplification? Is it computational speed? Could you give a quick sentence or two about that? Thank you.
Yeah, so a strong form is really easy, right? It's very easy to write down a finite difference stencil. And so people like that. It's also local. So if you want to do something fast and quick and dirty that will scale well, often a strong method is really nice. But in my experience, when I started getting interested in computational seismology, I knew that the finite difference method had lots of problems for earthquake seismology. So in earthquake seismology, as I said, you really care about topography and bathymetry. Surface waves are really important, so waves that interact with the free surface. And that's where a strong method often fails, because it cannot capture that dispersion accurately over large distances. So if interactions with a surface, either a free surface or an internal surface, are important, like Scholte waves or diffracted waves, that's extremely difficult to do accurately with a strong method. And so whenever you're in a regime like that, you want to avoid using a strong method. If you're just trying to propagate body waves through a medium, and you're not so concerned about what happens at interfaces or fluid-solid boundaries or the free surface, then a finite difference method will be just fine.
Thank you.
Go ahead, Luis.
Oh, hello. So I have a question related to the optimization slide you presented. It's particularly focused on how to construct the Hessian. Do you have to construct the Hessian? Do you have to store individual kernels for each station pair, or do you backpropagate the adjoint field from all the stations to the sources? Or how do you construct the Hessian?
Yeah, so in LBFDS, you sort of iteratively construct the Hessian, but you never construct the Hessian explicitly. That's the whole beauty about the LBFDS method. So actually storing a Hessian or calculating a Hessian is not in the realm of possibilities. But using this limited memory BFGS algorithm, you can get effectively the solution to H delta M equals minus G iteratively. That's the whole idea. That's a quasi-Newton method. Yeah.
Thank you.
Now, I mean, I didn't add a slide on this, but these days the solvers are getting so fast. And Etienne Bachmann, I don't know if Etienne is talking at this workshop, but
Not this one.
we now have solvers that are so incredibly fast on graphics cards that doing the inverse problem using Bayesian approaches is becoming feasible. So we're not very far from being able to do full waveform conversion using techniques that we used to think are just inconceivable. So I think very significant changes are coming also with machine learning and AI and pins physics in for neural networks. So yeah, it's always very rapidly evolving and quickly moving, and it's a really great time to be a part of that.
Well, one side effect of recording and having 186 people might be a little tentativeness in launching questions out in front of everyone, but we will I think have plenty of time to interact. And so unless there are no hands up or people want to ask anything, I think we'll thank Jeroen again here for giving us this start to the workshop here. And yeah, I don't know, I'm thanking him again. And we'll move on to Daniel, if you could share screen for the next talk here this morning or evening. Thank you, Jeroen.
Right. Good, let me try that. So I'm going to make it more fun, hopefully, and less heavy in terms of equations. Now, if I put this full screen, I hope you see the slides. And if I put this,
It's not yet full screen for us. We can see your cursor, so that's a good sign. Or we're seeing, you know, the full panels with the thumbnails.
right. So what did I do wrong? So did this one switch?
He says someone's giving a troubleshooting saying he needs to share his other screen in Zoom, but what we see is the thumbnails. I mean, we could watch the talk like this, but it's probably worth trying to
Right, let
get
me
the full
try
screen.
something else. That.
So I will give a short introduction, but Daniel Peters, lead developer for SpecFem and the professor at KAUST, King Abdullah University of Science and Technology in Saudi Arabia. Looks great, Daniel.
So this looks better?
Yeah.
Let's hope it,
Yep.
it works. So, right, so I was asked by you, Carl, to show you a bit about the SpecFem codes and start with the history of SpecFem and then quickly show you a bit about the codes, the current state of the development and some examples of the codes. So the history of SpecFem, so my own history, it starts about 2008 or something when I started working with SpecFem, and then more and more got involved with it. But the history here goes back to Dimitri, and so it's a fun way, maybe a brief history of SpecFem, how I would tell it, which starts something like that. So it's a cold and cloudy day in April 1995. And I looked it up, it was actually cold and cloudy. So that was April 4th. And you see streets of Paris were still crowded with cars, and Oasis was just on a tour in Paris. So that's about the time we started SpecFem, when Dimitri was basically sitting in a class given by Ivan Madej. And Ivan Madej was invited by Jean-Pierre Villatte to give this course at IPGP, where Ivan was working with Anthony Patera at MIT at that time. Maybe you recall that the spectral element method was basically invited by Anthony Patera in the domain of computational fluid dynamics. So Ivan was giving this course about the spectral elements. You see here, April 4th, 1995, where Dimitri sits in. And then he decides, together with Jean-Pierre Villatte, his thesis advisor, that they will code this up for seismic waves. And that was Dimitri's thesis then, basically. So his thesis, 97, was about the spectral element method. Now that kind of triggered then the interest of a young Professor Jeroen Tromp, you just heard, at Harvard. So Dimitri started working with Jeroen at Harvard, coming out with these really how we call it, seminal papers about the spectral element method in our domain for seismic waves. So that was 99. And then together they started implementing the codes, built a cluster for global wave propagation at Caltech. And you see, I like this play of word where the California Institute of Technology built a ground-shaking cluster. At that time, that was really something new. There were many groups having these kind of clusters in their basement, and Jeroen and Dimitri were just building things by themselves. So now we have global wave propagation on these clusters. And then just a short while after, the software they wrote wins the Golden Bell Award for the largest seismic simulation ever on the Earth simulator in Japan. So that was 2003. And now, as strong advocates of open source software, they shared these codes and put it into the hands of everyone interested, which is mostly the seismological community as SpecFem. So that's the codes you start working now with. So the code repository is SpecFem. They're all hosted on GitHub. So now we have SpecFem with these. I'm mostly showing you these three packages: SpecFem 2D, SpecFem 3D, and 3D Globe, all hosted on GitHub through the geodynamics, which is the CIG code repository. So I think the main message here is that the codes, the SpecFem codes, are community codes, and they have benefited tremendously from all these contributions from different researchers over the years. So it's no more just Dimitri and Jeroen involved in these codes, but more and more people came in, added contributions to it, etc. Now, I came in later, started doing more and more work on the SpecFem codes, and now have become kind of the lead developer and maintainer of these packages. But at the end, it's really about you. It's about the community coming up with new ideas, coming up with new contributions, and you can contribute to these packages as much as you like. So what are the flavors? So I think of it like ice cream flavors. So what are the SpecFem flavors? So we have this 2D, 3D Cartesian, and 3D Globe version, and they all have kind of slightly different flavors to it. So if we look at the 2D code, the features, obviously we have the PSV and SH membrane waves capability, but the package also has these 2.5D simulations that you can do, basically 3D axisymmetric simulations. In terms of materials, it supports acoustic, elastic, poroelastic materials. They run on unstructured meshes, so if you have trellis or qubit or GMES, can come up with your own mesh and then run these codes. CPML, the convolutional PML boundary, is something that is added in the 2D version, for example. Higher order time schemes are there as well, like Runge-Kutta schemes, etc. There's anisotropy attenuation and obviously also the adjoint kernel capabilities. And the 2D version supports CUDA, for example, so you can run it on GPUs. And again, many people contributed like different contributions to these codes. And so the 3D versions then have slightly different contributions, slightly different flavor to it. In terms of the Cartesian, which you can think of the box version, it's like, again, acoustic, elastic, poroelastic domains are supported. Unstructured meshes, again, load balancing is involved. We have all these coupling between the different domains, acoustic, elastic, poroelastic, etc. The convolutional PML is also in this package. We have a nice module, which is the fault rupture module. So you can run dynamic or kinematic fault rupture simulations with it. Again, is anisotropy attenuation, adjoint kernel capabilities. And then the 3D Cartesian version has CUDA and HIP support now for GPUs. And then the Globe version, you saw it before in the talk from Jeroen in terms of capabilities. So it handles 3D crustal and mantle models, has topography bathymetry in it for the ocean approximation, rotation ellipticity, gravitation, anisotropy attenuation, adjoint kernel capabilities, and the 3D Globe version now supports also CUDA, HIP, and OpenCL for different GPU hardware. So these are basically the 3 different flavors of SpecFem, if you want. And in terms of the more recent features that were added to it, where I was mostly involved with, is, for example, you can run the Globe version not just for the Earth now, but you can use it for running seismics on Mars, or if you want now also on the moon. And that would look something like that. So probably on Zoom, the video clip doesn't show very nicely, but you should see the wave field propagating over these planetary bodies now. And that's all in the Globe version. You have these examples. So that's kind of a new feature that you can use now, Globe, for planetary scale simulations, not just on Earth. And then another one very recent code feature was the HIP support. So this was added, for example, with Leopold Grimberg from AMD. He invested a lot of time and helped porting the codes that we have also to HIP. And HIP is, for example, important when you want to run your simulations on the upcoming supercomputer frontier. So if that one is going to be available, then you can use these SpecFem codes, the 3D and 3D Globe versions on Frontier now as well. Another feature Carl was, for example, asking for these local meshes in the Globe version. You can do that. So it does a cutoff of the mesh. It's no more just a full one chunk mesh, but you have these local meshes that you can do. And then something I added after looking at some of the moon problems on, for example, on Moon, but also on Mars, you have very strong scattering. So I added a simple way of adding scattering perturbations, which follow a certain distribution, like a von Karman distribution, into the Globe version. So this is still very crude way of adding these perturbations there. There is more work involved than to improve that, but that's something that is probably upcoming, and it's something I wanted to do for a long while. I keep delaying it, but that's local time stepping. We worked it out many years ago already. Now I want to really push this into the 3D Cartesian version, that you can do local time stepping and then do some mesh refinements, very local ones, and then hopefully local time stepping can give you nice improve ups in terms of the speed improving. So something important, for example, would be for fault zones where you want to have the mesh densely meshed around the fault, and then the local time stepping takes care of which of the size of the elements and what kind of time step you should have to keep the simulation stable. Then a few applications. I just picked out a few to give you a broad overview, not to be a complete overview, but just show you a bit what you can do with it. So if we look at the 2D code, just a very nice work I just discovered recently is using the 2D package for ocean acoustics. So it uses these 2.5D simulations, or the 3D axis symmetric simulations with the 2D package. This is work, for example, an application by Natalie and co-workers. Then
Es normal que uno a veces hable y ponga su posición y hable.
Please, sorry,
Pero ¿cómo hago yo para ponerme yo?
apologies, mute all. Okay, I just muted everyone. Now, Daniel, now I need to, can you unmute yourself, Daniel?
right. So I tried to unmute. You hear me again?
Yeah, sorry.
I come to noise simulations in a second, actually. So in terms of the 2D package, there's obviously the work with from Jeroen and Yukol and Jinya, which, for example, uses these classical SH and PSV waves to compute the elastic kernels. You can do that with the 2D package. In terms of the 3D package, I quickly show you here the work I was involved with, which is mostly highlighting the way how it works now with unstructured meshes, the 3D package. Before we had this very constrained measure that only worked for Southern California, then we tried to make it much more flexible than that. And then this work highlighted the way how it works now with unstructured meshes. So you can mesh in principle any geometry you like with hexahedrons, and then the code will work with it. And also the coupling between acoustic and elastic domains was a part of this work. And then Carl, you asked me to show this coffee cup simulation. That's this one here. So with the coffee cup, you see that we have a fluid domain inside the coffee cup, and then the cup itself is elastic, and the code can deal with the geometry, but also with the coupling, and it's just a very nice way, basically, right? And I called it Sesame because at that time we named the version of SpecFem 3Ds that was the Sesame version, right? And then in terms of globe, here are the noise simulations. So noise is maybe something I haven't seen that much in terms of applications with the SpecFem packages, but all the packages, they have this capability that you can run these ambient noise simulations with it, and obviously also compute the adjoint kernels for these type of problems, right? And that's basically all from my side. If there are questions, I'm happy to try and answer a few, but I will stop it.
Thank you, Daniel, especially for hitting all the things that we were hoping you could cover there. As before, so we're transitioning from sort of basic theory to history of the software, and we'll be diving deep into the applications here, but this is a great opportunity. So please, if you have questions for lead developer of SpecFem, you'll see his name on the GitHub issues, changes. These codes are run by human beings, and he's in front of you. So if you have any questions about SpecFem or the history, please raise your hand and ask. And I'll get things going with one. There was something in the chat. Okay, someone already answered that. So maybe I'll follow that up. So is the sun doable or has been done? Your three bodies were so impressive.
No, so for now we still keep this scheme of having an elastic mantle crust and then some sort of a fluid outer core and a solid inner core. So we did this for Mars, we did this also for the moon. That's something for future development where we can just get rid of this layout that we impose at the moment, right?
It is interesting because it's sort of the literature goes from like normal mode seismology in the 70s, and then quickly the same people like Woodhouse doing helioseismology, modes of the sun, but thinking about ambient noise images of the sun surface, and there's a lot, there's room to go back to the sun.
Right, it would be nice to bring it there, right?
Go ahead, Robbie.
Hi, quick question. I know that you're using, so you said that you can use Qubit in order to mesh the geometry. But do you use a different software for the visualization, or can you do it with SpecFem, for example? Do you use ParaView for the visualization?
Right. So we usually output, what we can do is for visualization, we output VTK files, and then you can look at them with ParaView or Visit, etc.
Okay.
So these kind of packages to visualize those files. Right.
Okay, thanks.
Any other questions? Anything in the chat we need? Okay. That was, oh, Jordan, go for it.
The question is actually on the build bot. If you could you give like a sentence or two about how that works with the whole software integration?
All right. So these packages on GitHub, when you submit a pull request, then there is first a buildbot check on it if it compiles. And buildbot was set up by David Lue in Princeton, so it's running on a server there. But at the same time now, we also check it with GitHub Actions. There are Travis checks which run and Azure checks now. So it's a whole bunch of simulations that are triggered when you submit a pull request to see if the package compiles, if the examples are still running. It's like this continuous integration and development cycle that we have. Right? So BuildBot is just a nice way to quickly interact from my side when I see the pull request. BuildBot tells me if it compiles, if it's okay from that side. And then if I look at the code, do the code review, then I can just quickly reply to BuildBot to accept it, and it makes a nice merge of the new contribution into the packages.
Thank you.
So there's a bunch of agents running and looking at your contribution, right?
Go ahead, Varun.
I have been using SpecFem for a few years now, and sometimes, it throws some error and I can't make any sense of it. And even when I, type that error in the Google, I hardly get, I mean, there are very few, solutions out there. So what is the best way to proceed? Whom to ask about such errors?
Right. So ideally, you would open an issue on GitHub. Something's not working. And then ideally, I hope that the community will come back to you and say, wait, I had this problem as well. I fixed it like that, etc. Often it stays in the issues. Nobody's replying. I try and reply for fine time. So sometimes then you will email me directly. Hopefully I reply, but I'm not sometimes always busy with other stuff as well. So I wish there would be more community support in dealing with these issues, right? But yeah, we do now a lot of these checks trying to make sure that it compiles on different operating systems, different compiler versions, etc. But yeah, I just recently found out that no, with the Cray compiler, now it starts complaining because newer versions of that compiler don't like something in it anymore. And checking it with Cray compilers is not done automatically at the moment. So yeah, we always run into these issues, right?
Okay, thank you.
Yeah, that was to be more direct, the people on this Zoom were kind of targeting new users or users who maybe haven't done the seismic imaging components or interface, but we survive through users, and in particular, like users who speak up and are, audible and GitHub issues and helping out. So Yeah, I think that's one of the message we'll be repeating here is just, it's almost like a recruitment session here to, the survival of the code itself hinges on having users, and in particular users who kind of transition toward super users and developers. So that's, we don't have any cartoon for that, but that's a trajectory that everyone should be thinking of, if they find research benefit from the code itself. Good discussion there. Any other questions here? I don't see any hands up, but if not, we will proceed, and there will be a break, especially if you have the containers working. If you don't, then during the break, we're going to try to get you up to speed. But yeah, thanks again, Daniel, especially for the time there and for putting the effort into the kind of slides that you will not see at AGU or anywhere, I think. So it's great to have a record of that history. All right, so I'm going to share screen now, and I'm happy to see people in the chat right now, and we'll get the slides to you. I'm pretty sure Daniel and Jeroen, we can find the slides and post them. Someone was asking. So we've got our two invited talks, and we're now transitioning to sort of like the slower welcome to the workshop. We'll get moving, don't worry. And so I'm going to introduce the team, and what we have here is starting with the UAF team. Brian Chow, introduced earlier. Julian Turin, postdoc. Amanda McPherson, PhD student. That's me. And I'll get my little laser bullet here. Yuan Tian, postdoc. Akash Gupta will be the hosts from UAF. And we're also joined by team from Colorado School of Mines, Ebru Bozdog, Ridvan, Andrea, and also Felix from University of South Florida, who was instrumental in our earlier Moment Tensor workshop, sort of a similar style of delivery of material. So those are the people you'll be interacting with in breakout rooms. Just wanted to put sort of faces on things, make this a little more human. I wanted to introduce just this, if you would say, the sponsorship for the workshop. The delivery of this workshop is most directly linked with a cyber infrastructure project called Seismic Computational Platform for Empowering Discovery. So I'm both kind of acknowledging the funding agency from NSF, where Ebru, Ian Wong, who developed or pulled together the containers and has been instrumental for this kind of delivery. This project's called Scoped. It itself will have larger scale. It's got kind of bigger objectives beyond SpecFem in terms of software, cloud delivery, HPC, and tools for the seismic community. But I kind of want to introduce you to this material because, as I said, it's both the funders, but over the next couple of years, we expect doing similar workshops. We had one on moment tensors, and this one's on SpecFem. And then eventually we're going to have these materials on a cluster. Instead of you doing it on your laptop, you would have access to the HPC resources. Okay, so here's sort of a layout. We're here to help you. We have sort of people tasked with managing certain parts. So I'm just like the master of ceremony or the Zoom host throwing out the polls. Brian's going to be running the tutorials for the most part. We also have, I should have put Akash Gupta will be running components as well, running the chat. We're going to have people. This is mostly for our organization, but then the breakouts, you'll be running into these folks. So that gives you a sense of who's on our end, as if we're kind of walking around the room and helping people. I wanted to put this out. This is off the website, but I think it's important to establish kind of what expectations might be going into this workshop. We had a lot of questions, and we started making this list of saying like, well, what are you going to get and what are you not going to get? There's a lot of things that SpecFem can do, a lot of things that different people are interested in. And so here's sort of what we are going to experience. We've got these lectures on the basics, running open source software from inside a user download container. That's what we'll be doing, small scale simulations. We will be doing iterative seismic imaging examples. That's something we've never delivered in these kind of history of these workshops. So that's definitely new. We'll be demonstrating the extension to 3D, how this works. Fortunately, it's basically one flag changed, but then you also need the computational resource to deliver that problem, but it's seamless in some sense. Introduction to the 3D code, we'll be running the Mesh-Run solver. Akash will cover that. Sort of a research-ready environment for small-scale 2D jobs. You can do research on these on the container that you have. And what will you not experience? Also worth kind of looking in here. We're not running on a high-performance computing cluster. We're not looking at, for example, interfacing with moment tensor source estimation or meshing complex problems, running SpecFem 3D globe, seismic imaging examples. These are potentially can be covered in a future workshop, and we're thinking about that where we would have access to different system. And so that'll kind of segue into this slide, which is just a way of thinking about how training can be done, this kind of seismological training. And I wanted to kind of walk the users here just through these questions to get an idea of not only how we got where this particular delivery is, but also what the future opportunities might be. So first question was, do you want access to HPC resources for all the participants? And so the answer to us for what we wanted to do was no for us. After that question, the question was, do we want to launch this in the cloud, like at Amazon Web Services or Jupyter Hub, or do we want users to install their own stuff on their own machines? So that's the local or remote question. If we went the remote question for Jupyter Hub, for example, the Iris Roses online training was done. It's actually hosted through OpenSAR Lab here at University of Alaska Fairbanks. It's a Jupyter Hub, Amazon Web Services, but it requires sort of personnel to launch that. The UNAVCO Geodesy training workshops are run through the same system. So that is an option we had. But here we are over on the local choice. And then we also, just to sort of emphasize, you don't have to have a Docker container to run SpecFem. It's probably the easiest thing for our workshop here. You can download this one thing that we've checked works on different platforms. But just to say, you could be on your Mac laptop, install files directly and compile. You might have Conda install, but so I want to sort of emphasize these choices because some people have different preferences. And on the other side, if you want HPC, just sort of thinking about local versus remote options for users. A lot of these, the star indicates you need to have an account set up. It's way more complicated at some level. The star indicates here getting an account set up. So these are things to think about for the future, but I wanted to give the landscape of here we are. There's different ways to do this, and we're very excited. It's a, innovative in some sense of how we're trying to deliver this to a lot of different users and machines at a very low cost. Okay, I threw out some questions and answers just to say, you can hosts, feel free to add to the Google Slides here, but I can't be on Zoom the entire time. Is that okay? Yes. If the workshop time is bad, will the material be recorded? Yes, that's the plan. We're recording now. Will the workshop run for 4 hours each day? I don't know. Probably it will, but if we wrap up early, we'll just quit. We're not trying to fill up 4 hours. Is the agenda fixed? Not exactly. If we can move things. Do you have to run all the notebooks? No. If you want to, you can just watch and listen. You can look over the solution notebooks. We certainly encourage you to run the notebooks, make sure things are working, and take advantage of the people who've developed them and are familiar with the codes. And you can be launching questions related or just involved in getting things working. So I'm going to give this is sort of like a couple of minutes just to welcome you into, before we launch into Python notebooks, giving you a sense of, I want to ground people that we're all over the world right now. I am right here, and Bryant is next door in my office. We're sort of, the UAF team is here. Colorado School of Mines is also distributed. In fact, Julian from us is out in Cambridge here, Ridvan's in Turkey. So we're all over the place, but this is one of my favorite perspectives for the sort of equatorial biased view of the world. But there's our Pacific plate, giving us sort of a grounded geoscience view of where things are. I'm going to give a plug here just for the campus here. I'm in this building. This is the Geophysical Institute. This picture is about accurate in terms of the time of year, although the leaves have now fallen as of the last week. And this is just sort of highlighting from our campus. If you were in person here in Fairbanks, we would be giving you, hey, these are the facilities that are around here. High performance computing. We have the Alaska Satellite Facility. There's acquiring large amounts of remote sensing data, corner reflectors, CDBTO infrasound array back in the woods. There's a global seismographic station, IU.cola. Shout out to Adam Ringler here from ASL, who's on the call and interested in SpecFem. And so here we have infrasound group, seismology, geodesy, Alaska Earthquake Center. There's an earthquake every 12 minutes here. If there's a really large one, we'll share it with you digitally or audibly. Anyway, that's just sort of an ad promo for those of you who are, I have to at least plug the university here in this opportunity. All right, that we are, I'm going to stop sharing. And that finished our welcome. And I think we were looking at, let me just check the agenda, but I think, sorry. Any other hosts can grab in there too, but I'm either we're going to shift to start the workshop or take a break and bring people up to speed. So under the key links, you can go to the workshop webpage and yeah, we're good here. So we have, actually we're almost 7 minutes ahead of schedule, but I'm gonna ask some questions. Does anyone have for the chat, or you can raise your hand and ask, does anyone have chats about the expectations for the workshop, or anything that would be of generic interest to everyone? Okay, if not, I'm gonna try out our first poll question. And the poll question is going to be, are you ready to move on? And the way to interpret this is to say, do you think you have the container working for you? And by working, I mean maybe seeing a Jupyter Lab screen and possibly even having run a couple cells that seem to work. So this is where things are important for us to understand. I'm going to launch this question. Are you ready to move on? That means, do you have stuff working? And we are expecting, especially people who signed up today and yesterday, there'll be some no's in there. Just say yes if you have it set up, no if you don't. And when we head to a break in 5 minutes, we're going to be focusing on the no people to one-on-one get Docker installed and get the container working. All right, launch the poll. So click yes if you think you've got things functioning and work. Things look super positive right now on our end.
Great numbers.
So we have at the moment, there's only 8 out of 130 respondents. So nevertheless, I think a 30-minute break would be just fine. And that'd give us time to get through. Okay, so if you haven't responded, we've got, slow respondents. If you're hearing this, open Zoom. There should be a question to find an answer to. And, but I think this is enough information right now. So we'll do, I can just share the results so everyone can see. We've only got 9 people actually, which means honestly, it's probably a source of pride that 130 out of 139 have this working, because it's a huge amount of work to kind of prepare the material and also get these containers working on a lot of platforms. So yeah, I'm sort of shout out to Bryant and Ian and everyone there. So I'll share the results. But anyway, I know a lot of you haven't responded. So either for those of you who didn't respond, stick around during the break. If you want to get things working, let's do that. There's only 9 of you who responded, said there's some issue to get sorted out. So we're going to call the next 30 minutes here a break. and Zoom will stay on. You can exit Zoom, you can come back, but in 30 minutes, we're going to start as the schedule shows here, with Bryant kicking off. So I think we're right on. Yeah, sorry, it's a little confusing. I'm 4 hours behind the schedule there, so I have to convert the time as well. But in 30 minutes, we're going to start in earnest on the materials with Bryant kicking off. So thanks for being here. You can leave Zoom, you can just mute yourself. And if you need any help, please stick around now. And so I think, how can we easily identify people who need help? I think what do you think, you guys? I was thinking we'd do a
Open
breakout
some
room.
breakout rooms. Yeah.
Why don't we just
Maybe
do,
if you need help, you can join one of those breakout rooms.
okay, and let's just say, anyone needing help, let's go into breakout room 1. There's a bunch of messages coming in, but hopefully people are covering them. Okay, so breakout rooms, we'll create right now, we'll just create 10 breakout rooms and let participants choose. So join the first breakout room if you have. I'm trying to think, do we really have to have a breakout room, or can we just do this in the main room right now? Let's just open the floor right now and ask who needs help with something. Actually, okay, I changed. Yeah, let's if you need any help right now, just speak up. Maybe that's the best start. You're in the main room and there's 9 of you needing some help, and we'll, as soon as we identify the issues, we'll join into the breakout rooms. You know what? Let's just do the breakout rooms. Get a smaller crowd. Join the breakout room.
Intimidating to talk in front of 150 people.
Join breakout room 1 if you have any issue, and the hosts will meet you there. So you should go down at the bottom, find breakout rooms, and click on 1. Okay, so we've got someone in breakout room 1, and I think, yeah, bunch of.
I can go there.
I think we'll get everyone in there and just discuss and find out what the main issues are.
Carl, probably you may want to pause the recording meanwhile the break, or
I'm so nervous about losing the recording that it's just gonna run. It's fine.
Okay.
I'm gonna go into the breakout rooms as well. So it'll just be a record of more realistic of what's actually going on. So we've got 5 people in the breakout rooms. If you're in the main room, and maybe someone can put in chat, just join the breakout rooms and find people. That's where help will be. I'm gonna actually go join them myself just to see. And then we'll probably parcel each help into individual rooms to get things going. All right, otherwise we'll see you back in 30 minutes, but we'll be here.
Can I do it? Okay. Can you see my screen? Yeah. Okay. So this is the error I received. And this is the Docker, so that I installed, but yeah, I don't know. Then I try to actually just run this on the Windows PowerShell.
Let me boot I'm gonna boot my Windows computer and try to check what's happened when I'm doing the same thing. I'll be back in a few minutes.
Okay, thanks.
Okay, can you check if you're running the Docker
servers?
Yeah. Docker is
Yes,
open.
ma'am.
Docker desktop, yeah.
And we may end up sort of splitting people into rooms once we figure out what the issues are.
Can you please go back to the error message? I wanna. Yes.
Maybe I'm trying to think in the interest of time whether we should split the PC from the Mac issues. Should we just ask Mac users to go to breakout 2? Brian, what do you think is most effective here?
Yeah, I think we
Yeah,
can
maybe
split it
that's
up by
better.
OS.
Okay, let's go.
Okay, I'm going to go to number 2 because I'm a Mac user.
Okay, Mac.
Me
then-
too. I guess it's better for me.
We do Linux in room 3.
Okay, let's
We're looking at Windows
broadcast
right now.
that. Linux 3, Mac 2, PC 1. Okay.
We'll come find you.
So Mac will be number 2.
Yeah, and we
Room number
can,
2.
I think we can broadcast to all. Let me just see. I probably have to be in the main room to broadcast. Anyway, everyone heard that, so, but we'll put it in the main room. PC 1, breakout 1, Mac, Linux, breakout 3. Okay, I will leave room, and I think the recording shifts with me, so
Mhm.
I'll be here,
Yeah.
hopefully.
I'm back. So I've turned on my computer, opened Docker,
So wherever I move, the recording moves. We were just saying that breakout room 1 will be for PC, 2 for Mac, and 3 for Linux. I don't know if that. Oh, it did broadcast from inside the. Did you see that, Amanda? That message reach you? I see in the chat that PC breakout 1, Mac breakout 2, Linux breakout 3. Just spell that out more. I haven't mastered everything on Zoom, whether I'm seeing a combined breakout or a full chat or.
Yeah, I'm kind of. Well, did you put that in the chat?
I put it in the chat from inside the breakout room.
So you'll always be able to see your own messages.
Okay.
No matter where they are.
Okay. I think in hopes that I will actually capture something a little more along the lines of what's going on, I'm going to go join one of those breakout rooms and just record, keep it recording.
Sounds good.
Let's see.
just speak up. Anyone?
How are
I can
things?
type in. You can type in chat if you don't have a working microphone or.
Where are we, Julian? Are we getting through hurdles?
So first issue has been solved
Okay, cool.
and waiting for the other one.
You mean there's no,
Hi,
Don't be, yeah.
yeah, so the issue that I'm having is that I actually installed the Docker in the desktop, but I joined the Zoom through my laptop. So I'm just kind of having hard time trying to communicate with you, but I think I did install the Docker, and I open it, and I don't know where to move forward from there. So I see that there are some tabs with containers, images, volumes, and develop environments. So what do I do next?
Your Windows, right?
Yeah.
So you should be opening the Windows PowerShell.
Mm-hmm.
maybe
So
share screen. What do you think, Julian? I mean,
I'm on my Mac.
no, not you, but he
yeah.
could. I mean, if you want to share your screen, you can, or we could talk through it, but
So I cannot share the screen because the stuff is installed in a different computer.
Got it.
And I'm joining a Zoom from my laptop.
Okay.
So and I try to join with this desktop as well, but it's not allowing me to join with two different devices. I don't know why.
Okay. So if you open your Windows, the Windows menu, and you type PowerShell, it will find it. And if you open that while the desktop Docker application is running, and you copy paste the comment that I've put in the chat, so Docker pull.
Okay.
So I don't know if you see it, otherwise I can repaste it. While Docker is running, you copy paste that in the PowerShell, and it will download the Docker image.
Okay. Okay, I'll try it. Thank you.
And Julian, as much as possible, if the commands you're providing are in a particular, it's probably at our install notebook.
Yes,
we
so
could
it's
also
here.
put those things in there, just to sort of, we're not.
All the instructions are right here.
Okay, and so really the question is like, is Docker installed for you guys? And the container download with decent internet takes 2 minutes. And then does it launch properly? So that question of like, do you see launch properly means you're kind of looking at that screenshot of the Jupyter Lab open, and ideally we try and make sure something works, can be run inside there. So yeah, if anyone in this room thinks there's a chance they could get things working and want to,
so once your download is finished, so that's the desktop, the Docker desktop app. Once the download will be finished, you'll have this image appearing here. So you'll have, if it's the first time you're using Docker, it's the first image that you'll have. And that's basically what contains all of the software we're going to be using during the workshop. It's the analogy is that it's the disk on which all the systems is written on, and the container will be the application that runs everything, kind of like similar to a virtual machine, basically. If there's any other problem.
we're assuming there's issues. If you're in the breakout room, until our goal would be to kind of clear people out of the breakout room if things are working, or if it just seems hopeless, but we're pretty confident we can help you because we've got 150 or so. Go ahead, Hale.
Julian, can I share my screen again? Because
no
apparently
problem.
the download is finished, and just to make sure if it's okay. So is this message okay?
Yeah, that's all normal.
Okay. So now, okay, perfect. Thanks.
So now what would be the next step? Now you're going to launch the Docker pull, or?
So the Docker pull's been done.
Okay.
And so now you can continue with the instruction. So I think with the Windows PowerShell, you should be able to do, let me check. You should be able to use those commands to create the directory in which we'll be working, and then do the Docker run to launch the container.
Julian, there's a chat about Microsoft Store to get Linux on Windows. Do we need that, or isn't that?
No, I don't think it's needed. So I think we have.
They received a message to install that actually separately and then restart my laptop after that.
Oh, okay.
Yeah.
Yeah, it might be, I guess, depending on the version of Windows you are. If it's not shipping with a Linux kernel, which I think most of the recent version up to Windows 10 and up, I think they all have a Linux kernel. I think otherwise, yes, maybe you'd have to install it.
This is good though, because we will take a note of this, and you know, with the numbers we have, we encounter sort of things that the group of 10 of us did not.
Yeah, so on the Docker page documentation, they say that you should be working on Windows 10 or Windows 11 to be able to run Docker.
And do you think that if you're on 10 or 11, you would not need what Hale, do you know what your Windows version is?
I'm on 10.
Okay.
So
Yeah.
yeah. But they've been asked to separately install the Linux for Windows and then restart. So yeah,
Okay.
I don't know, maybe there is something wrong with my machine, but
Yeah, honestly, I don't think I've been through this process while preparing for this workshop. I probably have installed Docker and like all the Windows, the Linux kernel and stuff like that, like way longer than that. So I don't actually remember what's needed to install Docker.
What was the issue?
When you're installing Docker in Windows, it requires to install basically some Linux kernel, I suppose, to be able to run the Docker backend. And some users don't have, one of the participants doesn't have access to the Microsoft Store to get basically the Linux updates.
Oh.
Is it free, or it's just the access? I mean, you don't buy
probably an access problem. No, I think it's everything is all free. But,
okay. That would be harsh. I'm gonna check the other breakout rooms. Just keep probing here. For I don't know, we may not be able to get over a couple of these, but these are some folks from GDMP community here. We'd like to help them out if we can. I'm gonna go to the other breakout rooms. Checking out the breakout rooms here. So 5.
Screen when you have the instructions for Mac. If you have the open up, you have the browser open for that page.
I don't think so. Let me share all my desktop instead.
Okay.
So I was looking upon these instructions.
Follow
Okay.
instructions I
So-
sent on the chat.
Exactly. Oh yeah, that's even better. So click on the link Andrea just sent you, because those are the instructions for downloading Docker.
Docker.
You already passed over it, so it's great. So let's move forward with the instructions for downloading the image and running the container for the workshop.
It was on an email, isn't it? The link.
I just joined it by this chat in a.
Oh, by chat. Okay.
Yeah.
Wait.
I kind of like the background audio.
Thank you. Sorry.
I don't know Spanish, so it's probably not bothering me.
Yeah, I can translate in real time.
It's my
about
grandma. My
it's about the
grandmom.
launch.
Yeah. Well, let me see if I can move to another space, a quiet space, and we can keep work on it. Can I?
Sure.
Yes, absolutely.
Thank you.
But
Are there other,
just okay.
Felix, are there, or Andrea, are there others in this room who would need individual help? Do you know, or are you just kind of going through one by one?
We're going one by one, but we could also do that and go
yeah.
to different rooms if that's needed.
Okay, why don't, well, we got 12 minutes, so have people all spoken up here about
I
what?
think George hasn't spoken up. So if George, you can talk about what your issue is, and maybe one of us can like go to a separate breakout room.
Yeah.
And it's possible people are in the room but not at their computer. It's hard. So if people aren't speaking up, we can't. But yeah, anyone should be speaking up if you want to try to get people to help you through to
George,
the.
sorry. George, are you there?
Maybe not.
Yeah, and even
sharing a screen.
Joa, are you there?
On Tila, yeah.
Okay, so it doesn't seem like so basically Rafael has this he's probably setting things up, and I think probably rest of one of us can stay here and others can.
Okay. I think I mean, just in numbers, we have at least something like 150 who are set up. So we do want to get everyone, but I think this is a good kind of target. 10 minutes, see who we can pull to the starting line here. So sorry for every time I move, the recording changes. So you'll hear that probably. Thanks, you guys. We'll see you in the main room in 10 or so.
Okay.
Okay.
Yeah, things are seem to be going well. Amanda, how's the chat going?
Pretty quiet.
Okay. Well, we'll start up in 10 minutes, and hopefully people will come back. I'll take a food break, turn off. All right. We've got some people in breakout rooms still. Actually, not really.
One.
Okay.
I just invited them to come back to the main room.
Okay.
Yeah, actually, I don't know if this is something that happens to you, but when I check the break rooms, I see the numbers. Like for instance, for me, room 1, it has 11 people, but of course it's not true. But I don't know if that numbers are.
Mine are, for me, they're not highlighted and they say not joined.
Exactly.
So it may be a function of,
Yeah, when they are not highlighted, it's that the people is not there anymore.
okay.
Okay, fantastic. Thank you.
I think we can just close
Mhm.
all the rooms. Yeah.
Yeah, gonna open them back up later.
All right. Well, Bryant, I think we're back from break. We've still got a strong numbers here and excited that a lot of you, the high majority of everyone still has things working. And if not, there's no problem just sticking around and watching. But I'll hand things over to Bryant that'll kick off the sort of technical part for the next, we've got 2 hours scheduled here. So I suspect we're going to use it. Hang in there. See ya.
Okay. Hi, everybody. I'm Brian Chow. I'm a postdoc here at University of Alaska Fairbanks. And I'm going to be leading through a lot of the workshop material for the next couple of days. So you'll be hearing my voice a lot. Akash also has a component. And so you'll see him either at the end of today or maybe tomorrow morning. So I'm going to share a screen and we're going to walk through how to get into our container so that we can access all of our workshop material. So hopefully you should be seeing a web page and a computer terminal. So that's kind of how we're going to need to get ourselves set up in order to get into the container. So this is the installation instructions that you would have gotten in that email from Carl. If maybe one of my chat hosts could put this link into the chat. So if anybody's not there, we can all get there together. And the idea is that we're going to follow some instructions in here in order to get into our workshop container. So I'm on this web page and I'm just going to scroll all the way down to the bottom to workshop days 1 through 3 startup procedures. So we're going to be doing the same thing every day in order to get into the container. And I'm going to walk through it slowly today, and then hopefully over the next 2 days, we'll be able to kind of either already be here or be able to run through this very quickly. So one important thing before we start is that you want to have Docker running on your computer already. So that's this first line here. Please make sure Docker is running. On a Mac, I would just go into Spotlight here and type Docker. And you can see that it's an application that I can open. You can see actually at the top, I've already got it running. For those on Windows, it's probably very similar. You would go to your search bar, type Docker, and start that application. And on Linux, you would use your terminal to start Docker. So once we've got Docker running, we're going to follow some instructions to open up our Docker container. So if we've already pulled our image, which is what we were doing in the break earlier or in the instructions for day 0. And the idea here is that we're going to run this set of commands. And one important thing I want to point out is that all of the workshop material that we produce over the next couple of days, we want to save it to our computers. And so we have to do kind of a special command when we run our Docker container. And that's the kind of first 2 lines is we're making some kind of empty directory where we can put all of the workshop material. So just to kind of caveat, this is a path on my computer, my local computer, that I am okay with creating and putting files into. You can use the same thing if you want, if you know that's an empty directory, or if, for example, you have other directories where you store your work, you're welcome to change that path. But for me, that's okay. So I'm just going to copy and paste one by one these lines of code and run them in my computer terminal. So I'm going to copy and paste. So this is just making that empty directory. where I'm going to put all of my workshop material. This is changing into that directory. So paste. So now I'm inside this SpecFem users workshop. And then this is a Docker run command that is essentially going to initiate our workshop container. And I'm going to copy the whole thing. Let me point out here also that these instructions are for Windows, Linux, and Mac Intel. If you've got a Mac M1 chip and you installed the M1 version of our container, you have just a separate set of instructions here. And if I'm going too fast, I'm sure Carl will rein me in. You're also welcome to do the slow down react or type in the chat that I'm zooming through this. And yes, if you're on Windows, you should be going from PowerShell. If you're on Linux and Mac, you should be going from the terminal. Paste. And I'll just break down this Docker run command just so that people kind of understand what they're running. I'll just do this once, and then the next couple of days we'll just run it. So the idea is that we are running our workshop container, which is this, this link right here. It's called Adjoint, and it's hosted on GitHub. You would have installed it already. We're opening essentially a Jupyter Lab instance, which is like a kind of computer Python environment, and we're going to run it on this port. That's -P. So it's just a port on your computer. And then the important thing is that because we want to save all of our workshop material on our local machines, we need to essentially connect the container to our local machine. So that's this mount command. The idea is that we're linking the working directory that we're in to a directory that's inside of the container. That's the home scoped work. So this /home/scope/work does not need to exist on your computer. This is exists inside of our workshop container. And this will make a little bit more sense when we get to the next step. So I'm just gonna hit run. You should see some output come out that's telling you that things are working properly. Likely I'll probably be one of the slower computers here because I'm running on a 2015 MacBook and also running Docker and Zoom at the same time. So hopefully that gives everybody a chance to catch up. And so if you've done everything correctly and you've been following along, you're going to be met with this series of web addresses. And what we're interested in is that bottom one. So that 127.0.0.1. Yeah.
This would be a good time for the poll. Let me throw a poll out there.
I think this is probably the bottleneck for everybody. Once we open this web address, we'll all likely be on the same page. So yeah, I think a poll is a good point here.
Okay, poll is the question of, are you ready to move on? Would be either, you may be past this, but do you see this URL? And if not, we're gonna see how many don't have it. So if you see this URL, or if you've already copied and pasted it and you're looking at Jupyter Lab, then answer yes. So you should see a poll. Some of this, I mean, I know if you're into this for the first time, you're like, why is this so complicated? I mean, the short answer is just that in order to make something bulletproof that works on a lot of systems, a lot of different machines, that's our goal. But if you're familiar, if the container is basically to have the highest level of success, but it does come with some new things. So we are looking at 9 people almost ready and 1 no. So that's worth, and 3/4 responding. So if you can respond to this, if you're hearing it, please respond. But there's eight people almost ready, and that's enough to try to actually wait for a second. So maybe why don't we just do a breakout room for the almost readies and help them through. So I'm gonna suggest, if you haven't gotten to this point, we're at 93% are saying move on. So I think we'll move on, but please join a breakout room and let us help you get up there. So, and then a couple will join. So I'm going to launch, let's see, recreate. Okay. So join, I would say just join breakout room 1, and a couple of hosts will find you there. if you're needing some help. And just a reminder, yeah, click breakout rooms, find room 1, scroll down, join. I'd say go forward, Brian.
Okay. So yeah, hopefully everybody's seeing what I'm seeing right now. So what we're going to do is open this web address in a web browser. I'm just going to copy and paste that into my web browser. And what you should be seeing is a Jupyter Lab interface open up. And this is really the meat and bones of the next couple of days. This is where we're going to do all of our workshop material inside of this Jupyter Lab interface. So I'm going to spend a little bit of time kind of walking us through what this looks like, introducing us to kind of how to navigate around here and where we're going to do most of our work. So I'm going to make this a little bigger so everybody can see.
Here comes another poll. Do you see, and the question is, do you see what, not do you see what Brian sees, but in your own computer, do you have Jupyter Lab open? So the ready to move on is whether you've got this thing visible. And that poll is coming right now. Ready to move on is yes, I've got this on my own. All right, we're ready. It's 100% of everyone responding. So
you have one person in a breakout room.
Yeah.
Okay.
If one of the hosts wants to join there. Okay. So that's good news. Everybody's looking at the same screen. And so you can kind of relax for a second. I'm just going to kind of tour around this Jupyter Lab interface. You're welcome to follow along. So essentially our container is like a virtual machine. It's like a computer inside your computer. And so it's got everything that, you know, a very basic computer is going to want. It's got a directory system here on your left side. Actually, I'm going to throw on my annotate. So you've got your directory system here on the left side. And like we said, we've got all of the software that we're going to use for this workshop already installed inside of this container. So we don't have to deal with any kind of installation instructions or compiling of code. So you can see we've got SpecFem 2D and 3D, which Jeroen and Daniel talked about earlier, already installed inside the container. We'll be using both of them for the workshop. Then we've got some Python packages, which create our Adjoint software suite, which I'll talk about throughout the workshop, essentially automated software for running SpecFem. Here we can see a couple windows. Probably the most important one is this terminal. We'll use that to do one command before we start running into our notebooks. And then I think what I want to really impress the importance of is this work directory. So this work directory, like I said, because we are trying to connect our local machine to our container, this work directory is the tunnel between the two. You can think of your container like Vegas. Anything that happens inside the container stays in the container. And if you close the container at the end of the workshop, or your computer crashes or something happens, any work that you've done outside of this work directory is potentially lost. And so as we run through our notebooks, all of the files are going to get saved to this work directory. So you'll be able to access them with your local machine, even if you remove Docker, uninstall the program, whatever. But if, for example, you like create a file, or you are running through the exercises and you want to save some of the files there, you're going to need to move those files into your work directory. So I'll just kind of illustrate an example here. I made a new file. I called it test. It's just a text file. Inside I can put hello world and save it. So if I were to shut down my container, I would lose this text file. If I wanted to save it though, I could copy and paste it into this work directory, which again is our tunnel into our local file system. Then if I go back to my terminal, I look in this directory that we have just created, the SpecFem users workshop. Voila, there is my text file, and it's telling me hello world. So that's just pretty important. again, all of the workshop material automatically is going to be saved into this work directory. But if you do some stuff on your own, or you have some things that are not saved in the work directory, please remember to copy paste that before the end of each day. Okay. So with that, I'm going to go back here. I think now what I want everybody to do is follow along with me. We're going to update our AdJdocs repository. And so AdJdocs is where all of our workshop material is stored. And due to the nature of the container, with the fact that we kind of built it before the workshop started, but we've been updating workshop material since then, we need to update essentially all of the workshop material. So what I want you to do is follow along with me. We're going to click on this terminal button, which is down at the bottom left. And we're going to run these commands that are inside of this installation instructions, which is update AdJdocs. So I'm just going to copy and paste that. And run that. I just can't do it. This is just from GitHub pulling all the updates for our workshop material, making sure that we have the latest versions of all the workshop material. And we're gonna have to do this every day whenever we start the container. We'll need to update AdJdocs. And you should see this screen with a bunch of plus and minuses telling you that the files inside have changed. Maybe that's a good point for a poll, Carl, just to make sure everybody was able to pull AdJdocs and is on the same page.
Okay.
We should be ready to go.
So yeah, did you run git pull? And if not, you may be needing to find the right path and so forth. But did you run git pull and did you get something look like that? There's a question. We've got 8. Let's see. So I'm assuming that people have Jupyter Lab open. So Brian, why don't you just walk through it one more time where you found the right path? And I mean, now when he types git pull, it's nothing will well, yeah, anyway, go ahead. We've got 10 people, so I think that's worth.
Yeah. So this was the command here at the bottom. It's just a cd AdJdocs and git pull. So I just copied that directly and pasted it into the terminal inside of my container. So we're doing everything inside the container at this point. Yeah, people are also showing that potentially if you've run, day 0 workshop material, you might have some changes inside of the container AdJdocs. If that's the case, you can type git stash before you run your git pull command. That will just essentially hide all of the stuff that you've done inside of that day 0 container, and then allow it to pull all of the latest material.
Go ahead, Rohit, you had a question?
Yeah, so I don't know if I'm at the right, if the git pull worked or not. Could you run git log one line just to check the hash?
Oops. Is it one line?
You have an extra minus.
Here.
Okay, thank you.
Sure.
I'm gonna launch the poll again. So the question is, did the git pull command work for you? And if not, we may send you to a breakout, which is kind of the way we can pull things along here. So relaunch poll. Did the git pull work for you? Okay, we're down to three people needing. So I would say, yeah, can you head to, if you're not there yet, just head to a breakout room, and then we'll move on. So someone will find you and help. Thanks.
Cool. So yeah, By now, we should all have the latest version of EdgeDocs, and we can make our way into our workshop material, which is all hosted in Jupyter Notebooks. So it's all, and I'll give a brief introduction of what Jupyter Notebooks look like. So we're going to navigate using the directory system here on the left. We're just going to click into EdgeDocs, Workshops, make this a little bit bigger, 2022 SpecFem users. And here you can see the directory of all of our workshop material. I'll just explain what this is. Each day we have a different Jupyter notebook, which has introductory material, cells containing code that will either run Python or run SpecFem itself from inside the container. We have different topics that we're going to cover each day. So today will be about forward simulations using SpecFem 2D. Akash may talk about some, we'll talk about some 3D examples using SpecFem 3D Cartesian. Tomorrow we'll talk about kernels and adjoint simulations like Jeroen introduced. And then the final day will be about imaging, doing some simple 2D imaging examples. Similarly, all of these notebooks have a completed counterpart. So if I click into that, you can see all of the notebooks are there as well. And essentially, I've just run through all those notebooks to make sure they work, and I've saved the run notebooks there. So if for whatever reason, you start falling behind, or if your computer, is not cooperating with you, or if you just want to check that the cells that you're executing are working as advertised, you're welcome to open one of these completed notebooks and look at the kind of section that you're interested in. And similarly, we have some exercises given if we have enough time during each day. Days 1 and 2 have a couple exercises where you have some tasks that we're going to ask you to run, like changing a velocity model, asking you to rerun forward simulations. There are some solutions there. Try not to peek if you're confused. It's always nice to scratch your head first, but the exercise solutions are there, especially if after the workshop you wanted to kind of see how things might be done. And so we're going to kick off with day 1A, this intro to SpecFem 2D. This is this second notebook here, and so I'm just going to double click on that, and it's going to open up my Jupyter notebook. Again, I'm probably one of the slower computers here. You can hear my fans whirring. My computer's trying to take off. Okay. I'll just spend a little time walking through what each of these components of the beginning of the notebook are. I'll walk you through what a Jupyter notebook looks like and how to run through it. And hopefully, by the end of the day, you'll be an expert in Jupyter notebooks, and we can kind of zoom through this during days 2 and 3. So welcome to day 1A. This is Intro to SpecFem 2D. The outline here is that we're going to learn about the SpecFem 2D repository that Daniel showed is available on GitHub. So we're going to learn to kind of navigate through the repository, understand the files and directories that are there. There are a lot of them, so it's kind of useful to understand which ones are important, which ones you need for your actual work. Then we're going to run the example problem that's kind of default available in SpecFem 2D, creates a mesh and runs a forward simulation, generates synthetic seismograms. And then we will run a forward simulation with a homogeneous half-space model. That'll be in day 1B. And the objectives here are really to understand SpecFem 2D, really kind of get a good feeling of what the directory looks like, what files are important, what you actually need to run simulations. That'll help us draw parallels for when you want to port over to SpecFem 3D or 3D Globe. These packages are very similar. There are some differences in the files that are used and the ways that you might implement it. So I'll kind of throughout the notebook, I'll make notes of where SpecFem 3D might deviate from 2D. And we're going to do a lot of things manually, especially through the entire workshop. We're going to, run adjoint simulations and forward simulations manually, just to kind of show you what the bookkeeping looks like, what kind of steps are required in order to get through these tasks. And it'll help us kind of better understand some automation tools that are available, like size flows. So these are just some relevant links. Again, these notebooks are hosted on GitHub. So if you click through here, you'll just get taken to the notebook on GitHub. And the completed notebooks here, and some quick links to SpecFem 2D and its manual in case you just wanted a reference there for the future. And finally, this last little bit is just telling us how to use Jupyter. So the idea here is that all of the code inside of a Jupyter notebook.
Hey, can I pause for a sec, Brian?
Yeah.
I was just going to ask. I think we threw that out in the pre-workshop survey, but for those of you here, I just want to get a hand for. How about this? The poll question is: have you? Yes, if you've used Jupyter notebooks before, and no, if you haven't. So that's what the poll question is going to be. So here we go. Relaunch poll. Yeah, it says, are you ready to move on? But the question is, have you used Jupyter notebooks before? Yes or no? So it's an interesting question to me, because sort of 5 years ago, everyone would be saying no, but we're at 10% no. So these instructions will be helpful if you've never seen Jupyter. And so that's worth it. 10% is sort of our nominal cutoff for slowing down. So we should do that. All right. Thanks.
Cool. For the other 90%, please bear with me.
Yeah.
I'm just going to run through some Jupyter quick tips. And hopefully these are things you're already familiar with. So yeah, the idea here is that all of the code that we're going to execute through the workshop is located in cells. So this is a cell here. You can see it's kind of a darker background. It's got some code in it. Right now, this is some Python code importing packages. These are some terminal commands. And yeah, the idea behind this is that this is just code at the moment. It hasn't been executed. And so if you want to execute it, you would need to actually physically ask it to be executed. So I'm just going to make an example here of a cell that does nothing, just waits. This is from Python code, and if I want to execute this code, I would click on it, and it would be highlighted. You can see there's like a little bar here, and the colors change. So now I know that I'm selected this cell, and to execute it, I want to hit this play button. If I hover over it, it'll say run the selected cells in advance. I can also use the keyboard shortcut, which is telling me to hit Shift Enter. But if I click this, you can see that this cell is now executing. You can tell that it's executing because there's a little asterisk here inside of the square brackets. You can also tell that the notebook is executing because there's a black circle here, and it's telling you how long it's been running for, which is 14, 15 seconds now. Yeah, and so if for whatever reason, you want this cell to stop, you can hit this stop button. Let me run it again. Hit the stop button, and it should send an interrupt to tell the cell to stop. If your fans start whirring and you're worried that you're going to blow up your computer, you're always welcome to hit that stop button. And then at the top, if you just wanted to run these notebooks on your own time, if you just wanted to, execute everything, you can hit this double play button, and that'll run every cell inside of the notebook. And then one last Jupyter introduction is that commands that start with the exclamation mark are bash commands. So these are things that you might run from your terminal. So here, for example, we're running ls, which is listing out the contents of a directory. And then commands that start with the percentage signs are Jupyter Lab commands. Yeah, okay. So I think everybody hopefully is now an expert in Jupyter Lab and is ready to learn about SpecFem. So we're going to start with section 1. This is the SpecFem 2D directory tour. This is going to be a lot of looking at text files, looking at files inside of a directory, and really just trying to understand what SpecFem, when you clone it from GitHub, what kind of files you're looking at. So I'm going to execute this first cell. If everybody wants to follow along, I'm going to click here and hit the play button. And I'm importing some Python packages, which we'll use to visualize some things later. We're going to change into the SpecFem 2D directory. So this is has been cloned in from GitHub, and we're just listing out some files in there. So here, hopefully you're seeing the same thing on your screen. You can see a bunch of files in here. It can be kind of overwhelming. There's a lot of files and long file names. I want to make a point here that actually this SpecFem 2D repository might be a little bit different from what you would clone from GitHub, because we've removed some of the larger files in order to keep our container size down, but more or less it's the same thing. So there's some, some directories here. There's some text files with some readmes and instructions. There's examples, and there's a default example in here. And so I'm just going to go through one by one in the next couple sections, explaining some of the more important directories and files that you're going to need for running SpecFem. So here I'm in section 1A, talking about this bin directory. So the bin stands for binary. And if I execute this cell, I can see what's inside of this bin directory. It's a bunch of binary executable files. These are essentially like instructions for SpecFem to tell the computer how to run the spectral element method. Essentially all of the math that Jeroen was showing you earlier today. These are the code equivalents of under the hood, how the computer is actually solving the simulations. Note that we've already configured and compiled the code. So when you download SpecFem from GitHub, you won't have these executables. You'll have to compile the code for your own operating system. But in order to make it a little bit easier for everybody to follow along and for us to kind of just jump straight into the applications of SpecFem, we thought it'd be easier if we had precompiled the code in these containers. And each of these executables performs a different function. We'll use a few of them throughout the workshop, but the kind of two most important ones that we're going to use today are this xmeshfem2d and xspecfem2d. Meshfem creates the mesh. So if you think about Jeroen or Daniel's talks, we saw a lot of like numerical grids. We had talks about slides about hexahedral meshes. So the idea here is that this is an internal mesh software that SpecFem uses in order to generate those meshes. And then SpecFem2d is the solver. It actually, solves the wave equation using that weak form of the wave equation, generates our synthetic seismograms for a given seismic source and a set of stations. So those are the two more important ones that we want to focus on. During later days, we'll talk about other executables, but I might just skip over that for now. And this is actually just how you would run the executable. So we've compiled these binary files with MPI, which is a message passing interface. So it's essentially a parallelized software for running these executables in parallel. Jeroen was kind of talking about how, because of the way that this formulation of the code, it's very easily scalable and parallelizable. So the idea is that we can run essentially the same simulation on many different computer cores in order to speed things up. So if we just run this cell, it's going to break. It's going to throw an error. Don't worry, that's totally expected. But it was just to show you, like, this is kind of the way that you would execute one of these executables. And the error is just telling us the fact that we're missing some input arguments. So yeah, just kind of be familiar with this as we run through the workshop. Whenever you see this MPI run and these executables, know that we're actually running SpecFem in that cell. And somebody has asked what the mesh looks like. We'll get to that in the next section. Good question. So this is section 1B. We're looking at the data directory inside of the SpecFem repository. And the idea here is that the data directory really just contains all of the information that you would need in order to kind of customize your SpecFem run, your simulation. The kind of most important files that I've realized in this data directory are the par file and the source and stations file. So par file is the parameter file. It really just contains, all of the parameters you would use to kind of control the simulation or customize your run. The source file, again, is defines your source, seismic source, defines the kind of locations and mechanisms like a moment tensor or a force. And then the stations file defines where you want to recover synthetic seismograms. And I'll have a nice little graphic later that kind of helps convey the difference between, the simulation and the output synthetic seismograms. And then I just want to note that in SpecFem 3D, there are different types of source files. So the source file here for SpecFem 2D is kind of specific to 2D. In 3D, we might use like a CMT solution file to define our moment tensor or our seismic source. And so I'm just going to execute this code block. And really what this is doing is just printing out all of these files I just talked about so that we can look at them a little closer. And the idea here was that we didn't want you to have to like jump back and forth in the directory system to open a file and close it. So it's a little bit easier to just execute this code block and see the directory structure, what the par file looks like, what the source file looks like. So if you've executed this, you should see a bunch of print statements. This is just showing us the data directory, showing that there are 2 files in there, this parameter file and source file. Here's actually what the parameter file looks like. This is the top of the parameter file. Comments are with pound signs and things like, there's a key and a variable. So there's the title of the job, and it's called Test of SpecFem 2D with curve interfaces. That's kind of the entire setup of the parameter file. It looks the same for 3D and 3D globe. And so really, if you're running SpecFem a lot, you're looking at this parameter file a lot. You're tinkering with it, changing individual parameters in there to kind of customize your run. And throughout the course, throughout the course of this workshop, we'll be making edits to the parameter file in order to customize our runs. Here's an example of a source file, very similar layout, comments, keys, and values. Here you can see the X and the Z components. Since we're in 2D, our domain will be the X and Z coordinates. So, and these are in units of meters, like the comments say. And here's the components of the moment tensor. Yeah, and kind of all of the different source files for all the flavors of SpecFem have very similar layouts where they're just defining a location and components that will help initiate the source during a simulation. And then finally, the stations. SpecFem 2D is a little bit unique in that it can define stations internally. So this is inside of the par file, and it's just defining kind of a line of stations. You can see we're asking for 11 stations that start at this coordinates and end at this coordinates. So you're just defining kind of a line there. And it's asking to put them at the surface. So it's just like receivers on the surface of your 2D domain. More commonly, you might use a stations file. Sorry. And that shows, and this is kind of how SpecFem 3D does it as well. So if you want to go into the 3D version, you'll be getting used to these stations files where they're just listing out station codes, network codes. These are used for labeling seismograms. And then X and Z coordinates in 3D. This might be latitude and longitude, or X and Z in your Cartesian coordinates. And then burial and elevation. So things like topography, or if you want like a borehole station. And so that really just controls the kind of 2D or 3D location of your stations. Yeah, so those are kind of the most important data files that you would use in order to customize your run. So how you would set your source and how you would place your stations in order to recover your synthetic seismograms. And then one more important directory is the output files directory. Everything that SpecFem kind of generates during the meshing or the simulation gets kind of dumped mostly to the output files directory. Things like log files, error messages, the actual synthetic seismograms, figures that SpecFem 2D might generate, these VTK files that Daniel was talking about. Most of it gets dumped into this output file. So after you run a simulation, this is usually where you're going to want to go to make sure things were working, or if they weren't working. And so if we run this cell, we're going to see that there's an error message there. And that's actually because we tried to run that executable earlier and it threw an error message. And so it's always useful, for example, if you don't have access to print kind of, if you're running on the cluster, for example, and you can't access the kind of screen to look at error messages, it's always useful to see where they've been output in the output files directory. Okay, that was probably the driest section. Thank you for sticking with me. I was looking at a lot of text files. From now on, we'll be looking a little bit more at pictures and stuff. So hopefully that is a little bit, yeah, funner to look at. So we're going into section 2, and this is running the mesher using XMeshFem 2D. I'm going to use two terms to kind of talk about meshing. The first one would be a mesh, actually. And that's like the numerical grid where you would define your coordinates. So Jeroen was talking about the fact that we use hexahedral meshes. It's kind of showing you like he had that figure of like an element that was split up into a bunch of smaller points. So this is kind of an example of a whole hexahedral mesh. So this is in 2D. You can see this is the x-axis and the z-axis. This is actually going to be the example problem that we run. And you can see that they're hexahedrals because they're deformed cubes. So you can see, there's a layer of cubes and they kind of deform in order to accommodate topography in this case. You can see some internal interfaces where the mesh, like the element sizes actually get smaller to accommodate different resolutions in your simulation. And you can see that there's boundaries for this 2D domain. And so we're not working in like a infinite domain. We actually have a finite domain here.
I'll just pause
yeah.
We're so used to 3D, we're calling them hexahedral, but in this case, they'd be quadrilateral or quad,
Gotcha.
you hear people. So yeah, that's all.
That's a good point. But these are hexahedrals, if I got that right. So this is a 3D mesh in Cartesian. This is something that I created in my work. This is for the North Island of New Zealand. And you kind of see, if you extrapolate that 2D slice into 3D, you can see this kind of rectangular domain. You can see the element sizes get larger with depth, which is something that Akash will go over in his portion of the workshop, kind of explaining how we essentially try to optimize these meshes to save on computational cost. And then this color up at the top is just representing topography and bathymetry. I think that's something that Daniel talked about, that kind of really importantly in a lot of like seismic simulations, we are often interested in the effects of topography and bathymetry on things like surface waves. And so we have the ability to mesh these into our 3D and 2D domains. So here in 2D, again, this was the topography, and then in 3D, again, topography and bathymetry. And so if we go into section 2A, we're talking about model parameters now. How do I actually like define a model and a mesh? So this is just staying in the SpecFem 2D directory, and now we're looking at the PAR file again. So in SpecFem 2D and in 3D, we can define model values inside of the PAR file. This is just a section of it, and really the important lines here that we care about are these four. These are definitions of model parameters, so actual elastic parameters that define Earth structure, for example. And I've just copied and pasted them down here to make it a little bit easier to look at and to explain what each of these numbers mean. So these are 4 different materials, and equals 1 to 4. They define differing densities, which is rho, p wave velocities, which are vp, s wave velocities, and attenuation. And so you can see actually that in this example that we're about to run, there are 4 different materials, and these definitions have no sense of space. So you can think about the model parameters as just, we're just defining material property that we think, defines our domain. And eventually we have to assign these materials to parts of our mesh. So at the moment, this mesh has no information about, the model itself has no information about what my P wave speed or S wave speed is. And the model itself has no information about coordinates. It doesn't know what part of the mesh it needs to be in or where it's supposed to be defined. And so in the following section, we're going to show how these two are combined. So we're in 2B looking at mesh parameters. And first, I guess before we assign the model, we need to create the mesh. And so these are internal meshing parameters. So we're using SpecFem. And these are defined inside the PAR file again. And here we can see some important information about essentially defining the geometry of the model. We're starting at 0 meters, going to 4,000, and we have 80 elements along the x-axis. I think Daniel talked about observing boundary conditions. This is essentially to try to approximate like an infinite space. We don't want, you know, our seismic waves bouncing off the bottom of our domain or off the sides usually. And so we're allowed to define some absorbing boundary conditions, but we do want them to bounce off the free surface, which is what happens in the real world. So we don't have a top absorbing boundary condition. And then this very confusing jumble of numbers is actually how we're assigning our model parameters into our mesh. So the format of each line, starting with NX, min and max, and then the Z value, min and max. So essentially we're just assigning elements with numbers. So you can see that from element 1 to 80 in the X direction and 1 to 20 in the Z direction, we're putting material 1. So you kind of have to get clever. You might need to write some scripts or maybe think about it, you know, with pen and paper. How do I assign different materials that I want into different parts of my mesh? And then you would code it up into these numbers here, telling SpecFem how to put these things together. And finally, one last file we want to look at is this interfaces file, which is defining the curved geometry that we saw in our mesh. So if I look at these numbers, these are just X and Z values defining the interfaces. So if I scroll up back to this mesh figure, you can see like the topography here and these internal interfaces, those have been defined inside the interface file. And it's essentially just telling us kind of the contact boundaries between maybe different parts of the mesh or where material properties might transition. And I'll make a little like a colorful figure. We'll make a colorful figure later to kind of illustrate what it looks like when we partition the mesh into different material properties. Okay, so now we're actually running stuff. Now we're going to start running the simulation. We're going to make a mesh first. We're going to run a simulation, and then we're going to try to visualize all the results we made. And we're just running the kind of default example problem out of SpecFem 2D, the one that comes straight out of the box. Like I said earlier, you can make edits to your parameter file using a text editor. If you were to navigate in the directory system and click on the par file, it opened up in a text editor, and you could change values. But just for simplicity, to keep everybody on the same page, we're going to use this sizeflows sempar command. Sizeflows, again, is this automated tool for running seismic conversions, but it has some utility functions to make it a little bit easier to work with SpecFem. And so the idea here is that this command really just makes edits or prints values from a SpecFem parameter file. So if I just run this command, I'm actually going to be printing what the model parameter is inside the par file, and I'm going to be changing a couple of parameters. And this is essentially the same thing as if you were to go in with the text editor and change parameters yourself. Just makes it a little bit easier to follow along. So you can see that we're running our default model, which means we're going to take model parameters from the parameter file rather than defining them externally using like a external tomography model. We'll cover that tomorrow about how I might use external files to define my model if you have like a very complex velocity model. We're changing the number of processors, that's mproc to 4. So we want to run this with MPI, we want to run this in parallel. We want to create database files. So SpecFem internally kind of defines its domain, the mesh and the model in these database files. In 2D, these can be in like ASCII format because 2D domains are typically can be very simple. When we start going to 3D, it gets really cumbersome to try to define a huge 3D domain in terms of an ASCII file. So instead, we typically tend to use things like Fortran binary files, which are a little bit more optimized for storing large arrays. And here we're just telling SpecFem 2D to do the same thing, that we want to store these Fortran binary files so that we can use them to look at our model later. And then we're also just saying save the model files in binary. And if you've been following along now, we're actually finally running something. And so here we're going to be running MeshFem. We're going to be creating our mesh using 4MPI processes, and we're just spitting out the log file to a text file so that it doesn't overwhelm our display. So maybe that's a good point to stop and see if anybody has any questions or has fallen behind, needs us to slow down.
There's tons going on in the chat. There are little fires getting put out, but it's great to see everything in chat. You can also raise your hand if you feel like asking questions as well. I can see how chat is efficient as long as your message doesn't get buried. And we'll do a poll maybe once there's some visible output to see.
Yeah, probably after we run the solver.
And we'll probably also take a break on the hour. I don't know, would 10 minutes get us to the end or no of this notebook?
We'll get close.
Okay, that sounds good.
Cool, and I'll just power through. So we've run our mesher. We've actually run mesh generation component of SpecFem 2D. I'm just printing out the top and the bottom of that file just so you kind of know what they look like. This is what, you know, a typical SpecFem output log might start with, just telling you that you're running what version and what kind of part of the code. And then at the end, for the mesher, it's just telling us this is going to be a parallel simulation. We're running on 4 cores. So that's what we wanted. And that kind of leads us into being able to run the solver with the files we just generated. And so I'll just kind of glance at some of the files that get generated. We're just looking at this output file again. And a certain part of it, you can see that inside the output log file, it's telling us that we're writing a stations file. And like I said earlier, since we're using that internal representation of stations, it's writing out a couple of lines of receivers. This stations file matches exactly and shows you the format of how the stations file should be set up. These are those database files. Again, like I said, these are the internal representation that SpecFem uses in order to run the simulations. You can see that we have 4 of them because we're running on 4 processors. So we partitioned our domain into 4 different sections, and they kind of talk to each other in order to complete the simulation. And then finally, Daniel talked about these VTK files. These are very useful for visualizing meshes, especially in 3D. Throughout this workshop, since we're using 2D, we can visualize things using Python. When you get into kind of larger 3D domains, you start needing external software tools like ParaView in order to view your mesh and your model, the kernels that you generate, etc. Yeah, that was the output of MeshFem, and now we're kind of ready to run SpecFem. And I just wanted to kind of talk about what's going to happen under the hood as we run SpecFem.
I'll do a poll while we're doing that too, just make sure. Question is, yeah, did you get those last files that Bryant was showing there? Did things work? I presume at some point we'll know the answer to that. But let's launch one just to get you engaged a little. The relaunch polls question is, did the meshing seem to work? Okay, going on. It's at 100%. So great.
So yeah, this is kind of just what a little info kind of graphic that I wanted to show in order to show the kind of counterpart between what's happening in a simulation and some of the results that you might get. So this is actually a 3D simulation shown at the surface, but I think it's just a good teaching tool. So this is actually a numerical simulation happening through that 3D domain that I showed earlier through the North Island, New Zealand. And you can see that when a simulation happens, a source gets initiated. So that was that black star here. And then seismic waves propagate outward through the domain that you've defined, through your essentially numerical mesh in your model. That seismic wave field is propagated everywhere in your domain. But the synthetic seismograms that you get out, which are defined by your station file, those are just kind of point recordings. Sorry, the station's up here, this black triangle, this upside down white triangle. So the synthetic seismograms you get out are just point recordings of the wave field as it propagates kind of past that location. So you can see that as the waves are coming past, this red trace is getting drawn out, which is the synthetic seismogram. So the idea being, you could cover this entire domain with stations and get point recordings of your wave field essentially everywhere that it's simulated. In this case, all that information is kind of getting discarded after the simulation, and I'm only left with the synthetic seismogram at my single recording location. So that's to say that these seismic simulations don't scale, the computational cost does not scale with the number of stations you use. But you can imagine if I had a second earthquake up here that was propagating at the same time, the waves would kind of interfere with one another and likely create a simulation that whose results I'm not super interested in. And so the idea being that when you have multiple events, each of them needs a simulation. And so the computational cost of these simulations scales with the number of earthquakes that you want to simulate. So yeah, that was just kind of a small infographic to try to illustrate that point. And also to try to illustrate what's going on under the hood when we run the solver in the next couple cells. So here we're just kind of going to look at some solver parameters really quickly before we actually run the solver. We can see that we're going to output this seismotype 1, which is a displacement seismogram in units of meters. There's also other ability to output velocity or acceleration, other parameters. And then another important value here is the fact that we're saving ASCII seismograms. And so the output of the seismograms is just going to be this ASCII file that's got time and amplitude. But there are, the ability to output other types of seismogram formats like seismic Unix or binary. But in this case, and usually I guess in my work, I try to do everything in this ASCII format. It makes it a little bit easier to read and plot for my work. And so here we're running the actual solver. This is again an MPI run command. Now we're running SpecFem2D, and we're porting the output file, the output log, to just a text file. So I'm going to run that. It's going to take a little bit longer than the mesher because we're actually running the simulation. If you think about this little GIF up here, this is actually what we're doing under the hood right now. You're running on your computer right now a numerical simulation that kind of looks like this. And in the next section, we're going to try to visualize what that looks like. We'll be able to see the mesh and the model in terms of the material properties and the wavefront and some waveforms. Somebody asked that SpecFem can account for events occurring at the same time. Somebody can correct me if I'm wrong, but yeah, that you can have multiple events occurring at the same time. And yeah, and so what's going on under the hood is we're solving the seismic wave equation using the source that we input and recording all of those synthetic seismograms at the receiver locations that we and we looked at the kind of the source file and the stations file that we that are being used in the simulation. And when this finishes, it's just going to output the top and the bottom of the solver log file so that we can make sure that things run properly. Again, my computer is trying to take off.
Bryant, what was the runtime without Zoom?
Should be like 15 seconds.
Oh, really? Okay.
Yeah. Just need a new computer. But yeah, maybe I can fill this space by talking about what we're going to do in the next notebook. So currently we're just running the example problem. It doesn't really give you an idea of how to set up a simulation or tweak parameters. So in the next notebook, we're actually going to take one of the example problems and look a bit about how to kind of set up your own simulation example. But I think this is a really nice introduction to the package because it creates a pretty complex 2D mesh and some nice images of wave field propagation that we're going to look at in the section 4. Okay, so this is the end. This is what you're expecting to see when your simulation finishes. That's the top of the output log file. That's the bottom, just telling us what the date and time is, and that title that we saw again. If we look at a portion of the log file, it just, again, kind of tells us some stuff that we should already know, the dimensions of the mesh that we just generated, the fact that we've got something like 5,000 elements inside that mesh. And also, you know, it's useful if you've got a really large simulation that the log file actually tells you how long it might take for it to finish. So it has a kind of internal estimation of how long the simulation is going to take. So, you know, if I'm running a simulation that's going to take 2 hours, sometimes I'll leave this log file open and watch it evolve to make sure that things are running properly. And really, I would kind of stress that in your own research, if you're running simulations and something doesn't look right, it's always useful to look at these log files. The writers of the code really put a lot of information in these log files, and you could totally figure out if things are going right or wrong, mainly just by looking at the log files. And then finally, looking at the bottom of it, just showing that we have saved our model output, so we can see that it's defined by some X and Z coordinates and some elastic parameters there, and we will plot those in a bit. So hopefully everybody has been able to run the solver. I think I was maybe the slowest one. And so now we're just going to look at the velocity model and the files that got output by SpecFem 2D to run the solver. Again, you can see this is the model that got output. It's like the database files split into 4 different sections because we're running on 4 MPI processors. So we ran that in parallel. They're all talking to each other. And so here in this section 4A, we're going to actually plot that velocity model. And this code block is all Python, and I can just run it and then walk through what's happening under the hood. So we are reading in the text files, defining the stations and source just so we can plot their coordinates. We're using a utility function inside of SciFlows to essentially read the database, the model files that were just generated and plot them. We're going to plot VS here. And then we're just plotting kind of a bunch of text things that we're going to use for educational purposes. And that'll be clear when I look at this figure here. So this is the model that we actually just ran through. Looks very similar to the mesh I showed earlier, that 2D mesh in section 2 or so. You can see the source is that yellow star. We've got something like 22 receivers. These ones are on the surface, and these are something like borehole stations. And this is defining VS in materials, so we can see 4 different materials. This one actually seems like a liquid layer or gas pocket because it has a VS of 0. And then 4 different interfaces. So here the flat bottom, and then 2 internal curved interfaces, and then topography at the top. And just to kind of reiterate that these were all defined in files that we just looked at. This was the material properties. We can kind of confirm that yes, material number 2 had a VS of 0, and I've called it 4 here, but that's probably number 2. And if we look at the interfaces file, I assure you that if you plotted these lines that are defined by these numbers, they define these internal interfaces.
Let me throw a poll out there to see how many people got this picture. Actually, is this so? Things have evolved over the last week. They're generating this picture, Brian?
They're generating this picture.
Oh, cool. Okay. Yeah.
Somebody asked a very important question. Why does the topography look different than the mesh? And that was good catch. It's because of the way I'm plotting this. I'm using like a contour function, and I think it's just interpolating like straight lines out of the topography. So this figure is actually a little bit wrong, and you caught my error.
Okay, so great. Over 100 people here have seen this, so don't take for granted you run a MPI simulation and mesh.
Yeah.
Wow.
You're 90% of the way there to that expecting. Somebody asked if I could plot VP. Yeah, I could totally do that. So I could just change this to VP, and hopefully that works. Here's your VP. I have not looked at this, so we're kind of on the fly looking at what this looks like. But we could see what it looks like defined here. So not sure what all this white is down here, but if you wanted to confirm, yeah, you could just change that parameter here to VP and then look at these values here to check. And then I'm going to go down and we're going to look at some synthetic waveforms. So if I look back at this figure, you can see that we've got 22 station locations and one source. And so we're expecting 22 different synthetic seismograms. These could each be multi-component seismometers or instruments. So they each could have multiple components to their seismograms. And indeed, that is the case. So if we look at the files here, the synthetic seismograms get output have this SEMD suffix or extension, and the D here stands for displacement, telling us that these are displacement seismograms. And we can see that for each station, they've got two components, an X and a Z component. And just looking at one of those seismograms as an X component, just to show that this is the 2-column ASCII file that I was talking about, where time is on the left axis to left column, amplitude is on the right. And this is just the top. So before time is 0, we have 0 amplitude. Probably a little bit more useful to plot that. So this is just a Python code block reading in that 2-column text file, plotting it out on a line plot. That's what the seismogram looks like. You can see by something like 1 second, the kind of direct or initial arrivals start to happen. And this is for station 1. So we can kind of confirm that station 1, this is station 1 up here, the top left, and the source is here. So it took something like less than 1 second for seismic wave to propagate in that distance. And we can see, we probably expect that station 22 has maybe should show like kind of the latest arrival. And we'll be able to plot a record section actually to try to confirm that. This is just another small code block to show a different way to plot things. Might be useful in the exercise later. We're just using a SeisFlows utility function, which under the hood calls OpsPy in order to plot this seismogram. So same thing, different format, but this is, if you use OpsPy a lot, you might be familiar with looking at seismograms like that. And then finally, in this last bit of this section is we're going to use our record section tool. This is in a package that we have called PySep, and RecSec stands for record section. And so it's just a kind of a command line tool that we can use in order to plot all of the synthetic seismograms together. And kind of the breakdown of this call is that we're just pointing this tool to all the synthetic seismograms, to some of the metadata, so where the source and station are, so that it can calculate things like distance and back azimuth. And then we've got some kind of plotting customization that just changes how the figures look. So here's that record section that we're going to make. And you can use this tool for also plotting seismic data. It's used for plotting like data synthetic comparisons, which we'll do in day 2, I think. And it just creates some output logs, tells us that it's reading in synthetics, and generates this nice little record section. I'm going to zoom out just so you can see it better. So hopefully you're seeing the same thing. It kind of makes sense, stations, here's the distance in this column. Distance is getting larger as we go down. You can see the seismic waves propagating outwards. You can probably see the kind of the different propagation speeds of the P and the S wave, and the really large amplitude of station 12, which is actually co-located with the event. And this is a nice way of kind of visualizing your waveforms, making sure that the simulation actually makes sense. That, you know, if you saw some weird wiggles here, or the kind of nice propagation wasn't apparent, you might wonder if something was going wrong with your simulation. And here's the last section of this notebook, where we're just going to look at these wave field snapshots. And so SpecFem 2D by default can output snapshots of the wave field. If I scroll back up, don't follow me, but if I look at this GIF, you can see that you can imagine that if I took a picture of this wave field at some random time snaps, you would get, you know, maybe some get some like JPEG files of what the wave field looks like at each time step. And so essentially that's what SpecFem is doing under the hood of SpecFem 2D. And so if I look at these images, just looking at different time steps, here we're just showing what the parameter that controls the amount of images you get. So this end step between output images is just telling SpecFem how many times it should be outputting these figures. So it's every 100 time steps, and our DT is about 0.011 seconds. So we're getting them every like 0.1 seconds. You can see that we've got this many images, and if we plot some of them, we can see if our simulation makes sense. So this is at time step 300, it's about like 0.3 seconds. You can see, just making my window a little bit smaller. You can see the domain again, the topography, the receivers, and the source, the propagation of likely the P wave and the S wave coming out. We go into a little bit further during the time step. Now we can see some reflections from the top boundary from the free surface. See some propagation of the P wave through a different material. You actually see the S wave not propagating through that material. What I'm assuming is some converted phases of the S wave. And for a really crazy picture, this is at about 1 second in the simulation. You can see there's a lot of reflections and kind of converted waves. But what I wanted to emphasize on this picture is these absorbing boundary conditions. So you can see on the right side and the bottom, actually the absorbing boundary conditions are nullifying the waves so that they don't reflect back into the domain. And actually station 22 here is inside the boundary and inside the absorbing boundary. And so if we looked at that record section again, we can see that it's a 0 amplitude seismogram. It's not, everything's getting absorbed before it gets there. Cool. That was the end of day one, A. And hopefully you were able to follow along. Hopefully you learned something about SpecFem 2D, and in the next section, we'll be able to do a little bit more about setting up a little simulation problem and running some exercise problems.
Brian, this is great. We're not done for the day. He's just saying we're taking a break.
Yeah,
but
day
so
one
we've got 1B and 1. Probably we will only get through 1B. But let's just take a 5-minute break. And yeah, come back in 5 minutes. Take a break, and yeah, it's great to see everyone engaged, and hopefully you're seeing, honestly, it's for a default, it's a pretty complicated default. It's showing a lot of the topography, internal boundaries. I guess I do have one question. I mean, is that the PML then? Is this PML? Is that why there's a gap on the side of the simulation and mesh, Ryan? Do you know?
I'm not sure off the top of my head.
Okay, I don't know whether that's visualization.
Yes, I think it is PML.
Okay, so the idea is that if it looks funny, the PML is like adding elements, and so it's kind of a nice check actually that nothing's going in there. But that's a pretty sophisticated boundary to implement, and frankly one I've never used before. So it's a lot of whistles and bells in this default. All right, yeah, so come back 5 minutes, maybe at the 20 past the hour. We'll see in a few, and you can stick around and ask questions, but probably we should give Brian a break here too. think we've got a minute or so, but I was just kind of with all the 2D questions. One thing that's somewhat interesting is that a lot of us don't use the 2D code very much, but recognize that for teaching how to use SpecFem and seismic imaging, it's by far a better option, you know, to try to tackle as many things as you can in 2D before, and that goes for training and research. But if you get the feeling that we're guessing at some answers in the chat, we probably are, because I'm speaking for most of the hosts here, at least at UAF, we don't use a 2D code.
Indeed, the 2D code provides a great way to demonstrate or set up a 3D problem as well. Of course, things can be pretty much different from 2D to 3D, but still, if you want to check something very quickly without spending too much time and computational hours, it's pretty practical.
Yeah, and the discussion about, you know, importing models from repositories, wouldn't it be nice if, you know, there was sort of an Iris EMC equivalent for all of these tons of different industry models you can just point at and import, and even with having meshing certain properties, but it's a challenge. Let's see, Bryant, you want to take over? And we've got, just to give a heads up, there'll be an email, there'll be a Google survey coming just to gauge participation. And when you do get that, or if it's in the chat, it's like 5 questions, but we need some record of whether people showed up and whether the things worked or not on the platform you have. So it will take less than 20 seconds to fill out. So either through chat or at the end, we'll get to that. But I think, Bryant, do you think that 1B would be the objective, and then we'll save Akash's for tomorrow?
Yeah,
okay.
I think that makes sense. Cool. So looks like we're a little bit past, so we're going to get into it. So hopefully you're still at the same page on this Jupyter Lab interface. We've finished all the tasks here, so we're going to move on to day 1B. You can just find that on your navigation bar on the left, just below where you probably should be already. I'm going to go on day 1B. The idea here is that we're going to set up a small example problem that runs a homogeneous half space. We're going to run a forward simulation through that just to kind of show you how to set up a little like a separate SpecFem 2D working directory. This is kind of how I've been used to using SpecFem 2D rather than running simulations directly in the repository. We're going to kind of show the important files and directories that we need to be able to run it outside of that cloned repository. And then there's an exercise at the end of here where you can kind of put your skills to the test. We'll ask you to kind of set your own source and station and run your own forward simulation to see if any of this information stuck. So here, yeah, we're in day 1B, running forward simulations, and the objective here is to familiarize you with actually editing source and station files, adjusting a velocity model, and running a simulation. These are the same as day 1A, so I'm going to skip through the links and the Jupyter quick tips and just get into section 1, which is setting up a SpecFem working directory. So hopefully everybody's here in day 1B, section 1. We're going to run these first 2 code blocks. This one is just importing some Python packages that we'll need again for visualization. And this one's pretty important. This is how we're going to set up our working directory. And this is actually going to happen inside of this work directory. Like I mentioned before, this is the tunnel into your local machine. So all of the material that we create in this notebook is actually going to be saved to your local machine. So I'm going to run that. At the end, it's going to put out a list of the directory I just created. And essentially what it's telling me, or what I'm telling you, is that there are kind of 3 directories that you absolutely need to run SpecFem. Everything else in that repository that we looked at in the previous notebook is useful. They're very useful files and directories, but are not kind of the key directories that we actually need to run simulations. So the three that we need are the bin directory, the binary files, the data directory, so what we use to tell SpecFem how to run a simulation, and output files. And with these three directories, you can actually kind of run SpecFem outside of the clone repository. And I like to do this in my own work because it keeps things clean. It doesn't affect the actual cloned GitHub repository. It allows you to like easily copy and paste a working directory so you can run like a separate simulation without having to carry around all the additional files that the GitHub repository would contain.
I want to just throw a comment in there too, that it kind of emphasizes just good practices of what you need and don't need. I mean, I go into SpecFem, monster repository, so much stuff, and I am scared to like touch or modify anything. I'm going to break it. So, here you're just saying, just copy these three things, the whole thing runs. It reminds you that, yeah, you don't need, a lot of the stuff, and it's just good. I like this approach and suggestion.
Yeah, and it helps a lot also if, for example, you get to the point where you might want to create a pull request and make some changes to SpecFem. If you've been running simulations inside that repository, Git's going to be really angry with you and be like, what are all these new files you've just created? And there's ways to get around that, but this just kind of simplifies the task of keeping things kind of partitioned and a little bit cleaner. So this is section 2. We're going to talk about the experimental setup. So we're taking one of the example problems that's available inside SpecFem 2D. This is actually Carl's 2007 an example from his 2007 GGI paper, and the entire example runs a small kind of adjoint simulation between a homogeneous half space model and a checkerboard model. Today we're just going to look at the homogeneous half space. In days 2 and 3. We'll explore that checkerboard a little bit more, and also explore kind of using external models to define your model inside SpecFem. So we have copied over, like I showed, the data directory from that example problem. And so if we look at it, you can see that it's filled with files. Things that we're familiar with: interface file, 2 power files, each one kind of corresponding to a different model, one of them homogeneous half space, one of them to checkerboard. There's 25 different sources in here, so we have our kind of choice of which source we want to use for simulations. And there's a stations file that defines something like 132 different station locations, and we'll be able to use one or all of those today and tomorrow. This is a new file here. This is a velocity model. It's actually just like a XYZ file defining material properties, and we'll look at that a little bit more tomorrow. But it's kind of a representation of how one might use external tomography models in order to run their simulations. So we just want to look now, here we're at section 2A. We want to look at the homogeneous half space model. This is defined inside the PAR file, like I showed in the last notebook. If I look at this, this is the kind of one important line. If you remember from the last notebook, we had 4 lines defining 4 materials. Here we've just got 1, so we've only got a single material here defining our entire model. And just understanding again those parameters. This is density, this is rho, EP, and VS, and then attenuation. And that's just kind of reiterated there. If we look at the mesh parameters inside this PAR file, we can see how the geometry is defined. So we're going from 0 to 480,000 meters or 480 kilometers in the X direction, split up into 40 elements with 1 region. So the single homogeneous model parameters. And then if we look at this interfaces file, we can tell what the Z direction of our mesh looks like. So there's 2 interfaces. Here's the bottom of the mesh, which is 2 numbers showing kind of, it's just a flat line. The topography, another flat line. So we're defining a square mesh, and then 40 elements in the Z direction. And so really, before we even run MeshFem, before we even run SpecFem, we have all of the information we need to be able to visualize what our mesh looks like. So that's exactly what I've done in this little code block here, this Python function that plots the homogeneous half space. Oh, someone's drawn over my screen. And yeah, you can see I'm just taking kind of the values that I read from the mesh file and the interfaces file, and I'm using those to plot a little representation of what we might expect our mesh to look like. Let's run that. Oops. And so just kind of to, oops. There you go. So this is what we might expect the mesh to look like. If we were to visualize, if we run SpecFem and we were to visualize, this is kind of what we would expect to see. A square domain going from the origin at 0, 0 to 480 kilometers at in the x direction and in the z direction. Each of these would represent an element, so one of those quadrilateral elements. And there's 40 on the x direction, 40 in the z direction. You're welcome to count if you'd like. We can plot our source and receiver geometry on top. So again, the same as we did in the last notebook. We're reading in the stations file and just trying to parse out coordinate information, reading in each of the source files, trying to parse coordinate information, and then plotting them on top of the homogeneous half space model. And so here is that representation. We can see we've got something like 25 events there, 132 stations. Just gives us an idea of what our experimental setup looks like, and might help you in the exercise trying to select sources and stations. The next code blocks will just show us the numbers of the sources and the numbers of the stations. Again, just to kind of help you visualize, you know, we've got 25 stations, sources, those are their numbers. We've got 132 stations, and this is going to be a very overwhelming amount of text that comes up, but it's just to represent all of the stations that we have. It's probably a better way to plot that, but it's useful to kind of, I mean, in my work, whenever I was, you know, running simulations, it's always useful to know exactly where my sources are. You know, usually in like a tomography paper, somebody's going to plot sources and stations as their first figure in order to set up the kind of the context of the problem. So yeah, now we're going to jump straight into running SpecFem. First, before we do that, we need to do some bookkeeping. SpecFem is going to look for a file called source and a file called stations. At the moment in our data directory, we have neither of those. We've got ones that have suffixes. And so just for this initial example, we're going to copy source number 1 as our source. Now I'm just going to make sure that that's correct. So it should say source number 1. Yep. And then we're going to choose our stations. There are 132, and I did say that the computational cost of the problem does not scale with the amount of stations. But just for this example, we're going to create only one synthetic seismogram. So we're only going to choose the first station in this file. So that's what this little code block is doing, just creating a stations file with only one station in it. And then we need to set up the parameter file. This is very similar to what we did in the previous notebook. SpecFem is looking for a file called par file. And so we just need to make sure that we have the correct file name there. Again, we're telling it that we want to use for processors. So we want to run this with MPI. And this is a new parameter here. It's called this use existing stations. It's just to tell SpecFem 2D that we want to use our stations file rather than its internal representation of stations. So I'll run that. Just change some, this is just changing parameters in the parameter file and setting us up so that in the next code block, we are able to run the solver. So you can just see SizeFlows is telling us, hey, I've changed this parameter from 1 to 4, and I've changed another parameter from false to true. And so here is the code block where we're going to run SpecFem. You'll see in a lot of the example problems, there's some bookkeeping that happens, usually clearing out output files and creating new ones, just to make sure that if you are running simulations kind of back to back, the files that you generate either don't get overwritten or they don't affect other simulation runs. So we're just kind of doing the same type of bookkeeping. We're running MeshFem and SpecFem back to back. It's because we don't really need to visualize the outputs of MeshFem at the moment. We can just run these together, and then we're going to output the solver log file. And I will put a caveat here that in SpecFem 3D, there is usually an intermediate step, either decomposing the mesh or generating databases. This is in SpecFem 2D. This is happening, I think, in the solver, but in SpecFem 3D, you just know that you might have an additional step when you're running kind of these executables. Somebody asked if you can define stations after the fact. I don't think so, because essentially your simulation, your wave field simulation has been kind of discarded afterwards. I think there are some options where you can save the entire wave field, but those get very expensive in terms of file overhead, because it's a lot of, especially for like large 3D domains. And somebody's asking, why does it take so long to change the parameter files? Yeah, it's not a well-optimized utility function. It's bringing in, I think it's doing a lot of import statements. So it takes a little bit of time each time, but that's something that we can optimize a little bit more. And so here is my output file. It's just telling me that this is done. And so just like in the last notebook, we can check that we've created a synthetic seismogram. We only expect one because we had one source and one receiver. Here's all the output files. Here's my single synthetic seismogram in displacement. We can plot it just using OpsPy. As well, these other code blocks will look at the forward wave, the wave field snapshots. So there is my single waveform. Here's a snapshot at something like 800 times step 800. I'm not sure what DT is at the moment, but there's a kind of like initiation of our source. Here's our receiver. Here's our source. And then you can see the kind of propagation of the wave field outwards through this homogeneous half space medium. And then kind of at a later time, the wave field passing past the receiver. So that kind of brings us into section 4, which is the exercise. So the idea here being, we set up this homogeneous half space problem. We ran a very simple example with just one source and one receiver. And so in this simulation exercise, we're going to ask you to define your own stations file. You can use Python or write it out manually, but to try to create your own stations file with maybe an interesting geometry, you can make like a uniform grid or something. We're going to ask you to change the source a little bit, put it in a different location, maybe change the components in the moment tensor, and then rerun the mesh and solver. And try to see if you can visualize the results with all of the code that, or all the tools that you've seen in the last couple of notebooks. And so just the important thing is that we want to execute this first code block, which will set up our working directory for SpecFem 2D. And the idea here being that we're getting the binary files, we're copying in data directory with all the sources and receivers, making that output files directory, and setting the bar file. And then each of these tasks has empty code blocks where you have some tasks that you need to generate. I've tried to put some reminders in there of parameters that you should be aware of. And then some tasks about making the station source and analyzing outputs. And again, you're welcome to, I think there's enough Python code in there that if you're not familiar with Python, you can like copy paste some stuff. If you're more comfortable using other programs, I think you're welcome to like use MATLAB off your own computer if it won't crash it while running Zoom and Docker at the same time. And yeah, there is a solutions guide here for those that get stuck or want to know how I would have solved the problem or would have written out these code blocks. It might be useful if you get stuck somewhere. Yeah, maybe that's a good time to ask if anybody has any questions about how we've gotten here so far or the material we've covered.
We could split people into 2 groups and do the 2 problems. There's lots going on in the chat. I mean, one reason for displacement is that you can always differentiate, and going the other direction is not nearly as straightforward. So even if you're making measurements on velocity, we're probably always saving displacement. Also, for example, static displacements would be another reason. You can get geodetic offsets. SpecFem, we don't talk about this, but you get static offsets when you run simulations. So if you're looking at your typical subduction zone slip model or something like that, your displacement seismogram will finish off, at a different place where it started from. And that's pretty useful byproduct of the dynamic wave field solve. Well, so Brian, we'll have a hard stop in 19 minutes, I think. We won't go over 4 hours, that's for sure. But I do think, everyone, has anyone given these tasks 1 or 2 a try? Anyone want to, or maybe I don't know, we could, there's a number of things. We don't have a ton of time right now. Maybe tomorrow, I mean, we could split up into like 5 rooms. I could just randomly blast people into 5 rooms or something, and then
I think it might be good to just maybe give us his homework and
give them his homework. Okay.
Do it on, see if people can do it on their own.
That's a good idea. It's not, nobody wants live homework. But yeah, let's leave it. Let's just have a complete open discussion here. You can go through chat, or some of these topics are kind of hard to catch up in chat. So let's take the advantage of the collective Zoom and either chat or discuss whatever topics are coming up. I mean, I can see themes in the chat. Some of them are technical, others are like, can SpecFem do this? I feel like the answer is usually yes, even if we ourselves haven't done it. But you can get a sense from that, from the default in 2D, that there's a lot of capabilities. Yeah, any topics? FK, question about comparing with FK. Certainly at one point when the SpecFem codes were run, they're benchmarked against other analytical codes, or semi-analytical codes where, you think that that's an analytical solution, but there are benchmarks against FK. And at the surface, I don't know. Anyone have an answer to that? For a station at the free surface, I would guess that an FK code would be okay, but anyone you can ask a question audibly if you want. I don't even think we need to raise hand here if you have a question. Or if you have a question about what's coming up in the next 2 days. As I said in the sort of workshop expectations, I would say, if you've used SpecFem before, what's coming now with the imaging part, maybe if that's new, you ought to give it a try, because I think what has changed in the last 15 years or so is that the workflow has gotten much better. I mean, what took someone years to try as a grad student now might take a couple days honestly. And it's not just that computers are getting faster, it's really that the workflow has gotten better. So that's something that is, I think, kind of custom to this workshop. I will see if I wanted to show one reminder slide here, and then maybe we'll just post the survey in the chat and sign off. It's pushing the limits of brain power to get 4 hours staring at computers code. So everyone's done a great job. There's 139 people still. So I'm sort of watching the Omori. No, I don't know, the decay with time here. Okay, so I want to show one slide or two, I guess. And then
Maybe while you're setting that up, I just wanted to make one remark. Below the exercise is a section 5. Somebody had asked about, like, is there automatic kind of bookkeeping tools if you want to run thousands of simulations? So I'm just going to put a plugin for SizeFlows, which is this automated workflow tool that we've been working with. And there's an example there at the bottom that you can run, which runs the SpecFem 2D on your computer for 10 different events. And this is just for a local machine, but SizeFlows has the ability to run on, clusters or on servers and using SpecFem 3D. And so kind of getting familiar with this kind of 2D interface and then moving into 3D and larger computers is the simplicity is kind of added in when you use SizeFlows.
all right, we'll put this view. Yeah, so a couple things I wanted to advertise. There is going to have a hybrid component to a developers meeting for SpecFem right before the SSA meeting in Toronto this month in a few weeks. I just wanted to sort of make folks aware of this. We'll have some. We're planning to have some hybrid sessions where people can just log in, but it will be in person. And Daniel and Jeroen, Ebru, Lorraine, Chinya, and I, and several of the hosts, and we'll be there in person. I just wanted you to be aware of that. And some of you, I think, we've tailored this workshop here today toward just new users or people who would be new to the imaging component. This workshop is aimed at people looking at where the future of SpecFem is, but it's also open. We hope that some of the information from this workshop might inform the direction of where to go. The whole point is we're trying to get a larger base of users. So that was a plug for that. And then the last thing, and I'll just actually, you know what I'll do is I'll put this in the chat. I'll put the survey in the chat, and sorry. It's also on the workshop webpage, so see who can find it faster, I guess. Maybe I'll just put the workshop webpage. You can find the link from there. Somebody, if you go to in the chat workshop webpage, there's a day 1 survey, and it'd be great if someone could verify that it opens for them. That's all I need to know. Give me a thumbs up if it opened. Okay, great. Yeah, I'll send an email too, but this really helps us. This is, as you can see, it's a shoestring in terms of execution. Bryant has put in a huge amount of time, but in terms of there's no travel costs here, but there is the time to build this up, and we really benefit from having a record of who participated. So yeah. With that, what else are we missing? Anyone from the hosts here want to add in? Please show up tomorrow.
Yeah, I just want to say thanks everybody for following along today. Tomorrow we're going to get into some Adjoint stuff. We're going to look at how to generate kernels, how to calculate some misfit, and maybe how to automate that with SizeFlows. And we've got a talk from Chinya Liu, as well Akash. Oh, Akash will also be doing his portion of the workshop, which is an intro to SpecFem 3D, showing you kind of the differences between the two packages and hopefully run a little homogeneous half space and layered half space model. So stay tuned for that.
All right, we're gonna close shop here. Thank you, everyone. We'll see you tomorrow, hopefully. Keep the questions too. Yeah, see ya.
Thanks, everyone.